Hello there and welcome to Just About Earth, where we take familiar things about our planet, follow them far enough into the past, and usually discover that Earth has spent most of its history behaving nothing like the world we know today. Tonight, we're going back to a time when one of the most ordinary parts of your life, the length of a day, was completely different. Right now, a full rotation of Earth takes about 24 hours. That feels so normal that we rarely think of it as something that could change. Morning arrives, afternoon follows, evening settles in, and after one complete turn of the planet, we call the whole thing a day. But very early in Earth's history, our planet was rotating much faster. Models of the young Earth-Moon system indicate that around the time the Moon formed, Earth may have completed a rotation in only about 5 hours. In other words, the entire cycle from one noon to the next could have happened nearly 5 times during a single modern day. Before we go any farther, have a look at the time where you are now. Maybe it is late in the evening and you're already in bed. Maybe it is afternoon, and this is playing in the background while you do something else. Or perhaps it is well past midnight, and you have reached that stage of the night when learning about the rotation of the early Earth suddenly seems like an entirely reasonable activity. Wherever you're listening from, think about how much we managed to fit into 5 hours today. You could leave home, travel across a city, have a meal, watch a film, answer a few messages, make several cups of tea, and still have time left over to wonder where the afternoon went. On the young Earth, that same amount of time could have contained an entire rotation of the planet. The sun could rise, cross the sky, disappear below the horizon, and begin returning again before a modern working day had even finished. If you enjoy these slower journeys through science, you can give the video a like and subscribe to Just About Earth. It helps other people find this quiet little corner of the internet, where we can discuss giant planetary collisions, molten rock, enormous tides, and other extremely relaxing subjects before bed. For now though, settle in and forget what your clock says for a while, because the further back we go, the less useful our modern idea of a day becomes. The first thing to understand is that a 24-hour day is not a permanent setting that Earth received when it formed. A day is simply the amount of time a planet takes to rotate once relative to the Sun. There is nothing in physics that requires Earth to complete that rotation in 24 hours. It happens to take roughly that long now because of everything that has happened to the planet since it formed. Other worlds make this point very clearly. Jupiter turns once in roughly 10 hours despite being the largest planet in the solar system. Venus rotates extremely slowly. Mars happens to have a day fairly close to ours, but that is not because rocky planets are supposed to operate on a 24-hour schedule. Rotation is a result of history. It depends on how a world formed, how material collided while it was growing, what struck it later, how its mass was distributed, and what gravitational interactions affected it afterward. Earth began forming around 4.5 billion years ago inside the disk of material surrounding the young Sun. At first, there was no finished planet waiting to be switched on. There were countless pieces of rock, metal, and dust moving around the Sun. Small particles collided and stuck together. Larger bodies formed and began attracting even more material through gravity. Over time, collisions created objects hundreds and eventually thousands of kilometers across. The process was violent because these bodies were not gently settling together. They could meet at enormous speeds, releasing enough energy to melt rock and dramatically reshape the growing planets. Those collisions also affected rotation. Imagine pushing the edge of a heavy revolving door. A push near the centre does relatively little, while a push farther from the centre can produce much more turning motion. Planetary collisions work on a far greater scale, although fortunately most revolving doors do not involve objects the size of countries arriving at several kilometers per second. When one growing planetary body struck another at an angle, the collision could change how quickly the combined object rotated. Some impacts could speed the rotation up, others could slow it down, and others could change the direction of the spin. By the end of planet formation, each world had inherited a complicated rotational history, from all the material that had joined it. For Earth, the most important event in that history appears to have happened near the beginning. The leading explanation for the Moon's formation involves a massive collision between the young Earth and another planetary body, often called Theia. NASA describes current lunar formation models as involving either a large impactor, perhaps around the size of Mars, or variations involving multiple major impacts, with molten and vaporized material thrown into orbit and later gathering to form the Moon. The exact details are still being studied, but the basic idea that the Moon formed from material associated with an enormous early collision is supported by several lines of evidence. Try to picture the scale of what that means. An asteroid impact large enough to cause global consequences is already difficult to imagine. The moon-forming event involved something much larger. A planetary body slammed into the young Earth, producing temperatures high enough to melt and vaporize enormous amounts of rock. Material was thrown away from the planet but remained trapped by Earth's gravity. That debris formed a hot disk around Earth and eventually collected into the object that became the Moon. The Earth left behind was not the blue planet we know. It was extremely hot, heavily disturbed, and rotating rapidly. That rapid rotation is where our 5-hour day enters the story. The current Earth-Moon system contains a particular amount of angular momentum, which is the quantity physicists use to describe rotational motion. When scientists work backward from the system, we observe today and model the aftermath of lunar formation. They find that the young Earth could have been spinning far faster than it does now. NASA material discussing the early Earth-Moon system has described a roughly 5-hour terrestrial day at that stage. This should not be treated as though someone has discovered a fossil clock reading exactly 5 hours, 0 minutes, and 0 seconds. There is uncertainty in reconstructing events from more than 4 billion years ago, and different moon formation models can produce different early rotational states. The important point is that an extremely short day of only several hours is physically plausible for the early Earth, and 5 hours is a useful estimate for imagining how different that world may have been. If Earth completed a rotation in 5 hours, the surface at the equator would have been moving around the planet's axis much faster than it does today. At present, Earth's equatorial surface moves at roughly 1,670 km per hour because of rotation. A 5-hour rotation, assuming a broadly comparable planetary size, would make that equatorial speed several times greater. You would not feel a constant wind simply because the ground was moving quickly. The atmosphere would also be rotating with the planet, much as it does now. We already travel around Earth's axis at high speed without noticing it, because nearly everything around us shares that motion. What would matter were the physical consequences of such rapid rotation? One consequence would be Earth's shape. Our planet is not a perfect sphere today. Its rotation produces a slight bulge around the equator and a slight flattening at the poles. The faster a planet spins, the stronger that rotational effect can become. Early Earth, rotating in only a few hours, would therefore have been more noticeably distorted than modern Earth. Gravity would still dominate and hold the planet together, so there is no need to imagine continents and oceans being thrown into space every afternoon. But the balance between gravity and rotation would have been different enough to affect the shape of the world and the way material was distributed across it. Of course, talking about continents at this stage is getting ahead of ourselves. Soon after the moon-forming event, the surface would have been far too hot and unstable to resemble the modern crust. A huge amount of impact energy had been converted into heat. Large regions of Earth may have been molten, producing what scientists describe as magma ocean conditions. The atmosphere would also have been radically different. There were no forests producing oxygen, no animals breathing it, no familiar clouds floating above familiar seas. Gases released from molten rock, and the planet's interior contributed to an evolving early atmosphere while Earth gradually cooled. Now add rapid rotation to that picture. In approximately 5 hours, the planet turns completely around. A point near the equator passes from the side facing the sun to the side facing away from it and back again with remarkable speed. Under a simple equatorial example with equal day and night, daylight might last only around 2.5 hours, followed by roughly 2.5 hours of darkness. The exact pattern would depend on the geometry of Earth's orbit, its axial tilt at the time, latitude, atmosphere, and other conditions. But the basic pace would be startling. Sunrise would not lead into a long modern morning. The sun's apparent motion across the sky would be much faster because the ground beneath the observer was rotating much faster. Imagine, purely for comparison, that you somehow had a safe place to stand and an equally miraculous way to survive the temperature, atmosphere, radiation, impacts, and every other inconvenience associated with visiting the newborn Earth. You look toward the eastern horizon and see the sun rising. On modern Earth, several hours pass before it reaches its highest point. On a 5-hour Earth, the whole visible journey across the sky is compressed. Shadows change quickly. Noon arrives surprisingly soon. The sun drops toward the opposite horizon, darkness follows, and the stars begin moving across the sky at a pace that would seem completely wrong to anyone used to modern Earth. You would barely have time to complain that the day was getting away from you before it actually did. There is another object in the sky that would make the scene even stranger. The moon was much closer to Earth in the past. Today, its average distance is about 384,000 kilometers, but measurements and orbital models show that the moon has been gradually moving away from us as Earth and moon exchange angular momentum through tides. Laser measurements using reflectors left on the lunar surface show that this recession continues today at roughly 4 centimeters, or about 1.5 inches per year. That is tiny on a human scale, but spread across geological time it becomes an enormous change in distance. A closer moon would exert much stronger tidal forces. Tides are not created simply because the moon pulls on Earth. They arise because the moon's gravitational attraction differs across the planet, producing a stretching effect. The side of Earth closer to the moon feels a slightly stronger pull than Earth's centre, while the far side feels a slightly weaker one. This difference produces tidal deformation. Modern oceans respond dramatically because water can move, but the solid Earth itself also deforms under tidal forces. When the moon was much closer, these effects were stronger. This interaction between Earth and moon is also the main reason the 5-hour day did not remain 5 hours. Earth rotates more quickly than the moon currently travels around it. As the planet turns, tidal bulges are carried slightly ahead of the direct Earth-Moon line. The moon's gravity pulls back on those bulges, applying a torque that slows Earth's rotation. At the same time, the bulges gravitationally pull on the moon in a way that transfers angular momentum to its orbit. The result is that Earth spins a little more slowly, while the moon moves a little farther away. NASA describes this same process as the reason both the Earth-Moon distance and the length of Earth's day have increased over long periods. Nothing about that process is fast enough to notice while lying in bed tonight. Modern changes in Earth's rotation are measured in milliseconds, and shorter-term variations caused by the atmosphere, oceans, core, ice, and other mass movements can temporarily complicate the trend. Over very long periods, however, lunar tidal friction has been a major cause of Earth's rotational slowdown. NASA's Goddard material notes that tidal friction from the moon produces the long-term braking of Earth's rotation, even though other geophysical processes can make individual years behave a little differently. If you could watch billions of years of Earth-Moon history at high speed, the change would be obvious. Near the beginning, Earth spins rapidly and the moon sits much closer. As time passes, the Earth-Moon system gradually rearranges itself. Earth loses rotational speed. The moon's orbit expands. The length of the day increases. There would be no single morning when a 5-hour day suddenly became a 6-hour day. Instead, each rotation would differ from the previous one by an amount far too small for any imaginary observer to notice. But geological time is extremely good at turning tiny changes into large results. The same principle appears everywhere in Earth's history. A coastline can retreat grain by grain. A mountain can rise a few millimeters at a time. Continents can move at about the speed fingernails grow. None of these rates sounds impressive when measured over an afternoon. Give them millions of years and oceans open, mountain ranges form, entire landscapes disappear. Earth's rotational slowdown belongs to the same category. The effect of one tide is tiny. The accumulated effect of tides operating over billions of years help transform a world with days lasting only several hours into one with a 24-hour rhythm that now organises human life. That also means the number of days in a year has not always been the same. A year is set mainly by Earth's orbit around the Sun, while a day is set by Earth's rotation. If Earth spins more quickly but takes roughly the same amount of time to complete an orbit, then more rotations fit inside that year. At a 5-hour rotation period, something close to the modern length of a year would contain well over 1,000 rotations. It sounds as though everyone on early Earth would have been constantly changing calendars, but of course there was no one around to care. The universe does not divide time into Tuesday afternoons. Those are our labels. Earth simply rotated. The planet moved around the Sun, and the Moon moved around Earth. Even much later in geological history, once Earth's day had become considerably longer than 5 hours, it was still shorter than the modern 24 hours. Researchers can sometimes investigate ancient day length using geological records that preserve repeated tidal or biological cycles. Certain sedimentary deposits can record tidal rhythms, while some fossil organisms grew in daily and seasonal bands. These natural records act a little like old calendars written into rock and shell. They show that Earth's rotation has continued changing over deep time rather than remaining fixed. The rate of change has not been perfectly constant either. It would be convenient if we could take today's lunar recession rate, run it backward at exactly the same speed for 4.5 billion years, and produce a simple history. Earth rarely makes things that easy. Tidal dissipation depends strongly on the arrangement of oceans, continents, water depth, coastlines, and even the internal properties of Earth and Moon. As continents move, ocean basins open and close, and coastlines change. The efficiency with which tides remove rotational energy can change as well. So scientists reconstructing ancient day length have to combine astronomical physics, geology, numerical models, and evidence preserved from particular periods. There is also a useful distinction between saying Earth was spinning rapidly and saying everything on the surface was happening rapidly. A short day does not mean geological processes suddenly become 5 times faster. A volcano does not erupt more quickly simply because sunset comes sooner. Radioactive decay does not check the local day length. Chemical reactions follow their own physical conditions. What changes directly is the rotational cycle, and everything strongly influenced by rotation. The pacing of sunlight and darkness changes. Atmospheric circulation responds differently. Ocean circulation is affected. Tidal patterns are very different because the Moon is closer and the Earth-Moon geometry is different. Once life eventually becomes established, biological systems also have to operate within whatever day-night cycle exists at the time. Rotation has a major influence on atmospheres because it affects moving air through the Coriolis effect. On modern Earth, large-scale winds and storms curve because they move across a rotating spherical surface. Faster rotation tends to organise atmospheric circulation differently, though reconstructing the actual weather of the extremely early Earth is difficult because so many other conditions were unlike today's. The atmosphere had a different composition. The sun was younger and fainter. The surface was much hotter during the earliest phases, and recognisable oceans and continents developed over time. So it would be misleading to imagine a modern hurricane simply spinning 5 times faster. The entire climate system was operating under different conditions. This is an important point because it is tempting to picture the 5-hour Earth as our current planet with the playback speed increased. Keep the blue oceans, green continents, white clouds, familiar moon, and normal animals, then make the sun race across the sky. That picture is easy to imagine and almost certainly wrong. The period when Earth's rotation was extremely fast belongs to the earliest part of the planet's history, when Earth itself was still undergoing enormous physical changes. The Moon had only recently formed. The surface was cooling. The atmosphere was evolving. Frequent impacts continued. The solar system contained far more leftover debris than it does today. The world did not merely have shorter days. It was a younger and much more violent planet. Even the sun was different. The young sun produced less total energy than the modern sun, creating what scientists call the faint young sun problem when they try to explain evidence for liquid water on ancient Earth. Earth's atmosphere, greenhouse gases, clouds, surface conditions and other factors all become important when trying to understand how the early planet maintained environments where liquid water could exist. That puzzle concerns somewhat later stages than the immediate aftermath of the moon-forming impact, but it reminds us how many parts of the Earth system were changing at once. There was never a moment when scientists could simply adjust one setting called day length and leave everything else unchanged. The Moon itself was changing rapidly as well. After forming from hot debris, it had to cool and differentiate internally. Earth's gravity strongly affected it, especially while it was nearby. The Moon eventually became tidally locked, meaning its rotation settled into the same period as its orbit, so that essentially the same hemisphere faces Earth. NASA notes that tidal lock-in occurs because gravitational distortion and internal energy dissipation gradually slow a moon's rotation until the rotational and orbital periods match. At the same time, tidal interactions continued pushing our moon outward. So when we ask what Earth was like when days lasted only 5 hours, we are really asking about a brief window into a much larger mechanical relationship. The 5-hour rotation was not an isolated curiosity. It was connected to the giant impact, the formation of the Moon, the amount of angular momentum in the Earth-Moon system, the distance between the two worlds, and billions of years of tidal interaction that followed. The modern day is one frame in that continuing process, not the final setting of a clock that has stopped changing. Earth is still rotating differently from one day to another by tiny amounts. Winds move mass through the atmosphere. Ocean currents shift water. Ice melts and redistributes mass. Motions inside the planet affect rotation. Even large earthquakes can alter Earth's mass distribution by extremely small amounts. Over longer periods, tides continue to provide a braking effect. Recent NASA research has also shown that climate-driven redistribution of ice and water can measurably influence Earth's rotation, although these modern changes are tiny compared with the enormous difference between a 5-hour early day and the day we experience now. That makes every 24-hour day a kind of temporary arrangement. It is very stable from the perspective of a human lifetime, which is all we normally need. Your alarm clock does not require a model of lunar orbital evolution before it rings in the morning. But over geological time, the length of a day is another changing feature of the planet, just like the positions of continents and the composition of the atmosphere. And perhaps that is the easiest way to begin imagining the young Earth. Do not start with molten rock or giant impacts. Start with something as ordinary as sunrise. Today, sunrise is followed by hours of morning light. On a very rapidly rotating Earth, the sun would already be making noticeable progress across the sky, while a modern breakfast was still being cleared away. Darkness would arrive quickly, and another sunrise would never be far behind. Above that rapidly turning world, a much closer moon would pull strongly on the planet and begin the extremely long process of slowing everything down. The 5-hour day was therefore not a strange exception that needs to be separated from Earth's later history. It was the starting condition for a relationship that is still operating above us tonight. The same moon that now takes weeks to circle Earth once occupied a much closer orbit. The same Earth that now turns at a comfortable 24-hour pace once spun several times faster. The same tidal interaction that changes our rotation today was already working then, only under far more extreme conditions. But knowing that Earth rotated once every few hours still does not tell us what it would actually have looked and felt like to stand beside that world. To understand that, we have to remove almost every familiar feature of modern Earth and rebuild the scene from the ground up. The surface beneath that racing sky was hot, unstable, repeatedly reshaped, and in the earliest period possibly covered across enormous areas by molten silicate. The atmosphere above it was developing from gases released during impacts and from Earth's interior. The Moon occupied far more of the sky than it does now, and the young solar system had not yet settled into the comparatively quiet arrangement we see today. Once we place all of those pieces around the 5-hour rotation, the young planet begins to look much less like a faster version of modern Earth and much more like a completely different world that happened to become our own. Once Earth is placed back into that much faster rotation, the next problem is trying to picture what the planet itself would have looked like beneath the moving sky. The temptation is to imagine modern Earth with everything accelerated. Familiar oceans, recognizable clouds, perhaps a few continents, but with the sun rushing overhead every few hours. That image is useful for understanding the rotation, but it's not a realistic picture of the world that probably existed when Earth's day was close to 5 hours long. This was an extremely young planet. The Moon had only recently formed, the surface had been heated by one of the largest collisions in Earth's history. The atmosphere was going through major changes, and the interior was releasing enormous amounts of heat. For at least part of this early period, Earth may have had a global or nearly global magma ocean, produced by the energy of accretion and the moon-forming impact. NASA studies of this stage describe temperatures high enough to melt and even vaporize silicate rock, followed by cooling and condensation as the post-impact planet settled down. So let us begin with the ground, assuming we can call it ground at all. Immediately after a giant impact, standing on Earth's surface would not have been an option, even with extremely ambitious footwear. Large parts of the outer planet could have behaved as molten silicate rather than solid rock. Silicates are the minerals that make up most of Earth's rocky mantle and crust today, but under sufficiently high temperatures they melt into magma. Instead of isolated volcanoes releasing lava onto cool landscapes, the young Earth could temporarily have had molten material extending across enormous regions into great depths. The surface would have been losing heat into space while hot material from below circulated upward. Convection inside a magma ocean could transport heat efficiently, bringing hotter material toward the surface while cooler material sank. In that sense, the planet was already behaving like a system, moving energy from its interior towards space long before there were continents, weather forecasts, or anyone worrying about whether a volcano was likely to inconvenience a flight. It is important, though, not to leave Earth permanently trapped in this molten condition. The Hadean, the earliest recognized interval of Earth's history, lasted hundreds of millions of years, and scientists no longer picture the entire period as one uninterrupted ocean of glowing lava. Evidence from very ancient zircon crystals suggests that liquid water and relatively cool surface conditions may have appeared surprisingly early. Some zircons more than 4 billion years old carry chemical signatures consistent with interaction between rock and liquid water. That means the young Earth could cool from extreme post-impact conditions much more quickly than the popular image of a permanently molten planet suggests. Later, large impacts could heat parts of the surface again, and volcanism remained important, but early Earth was capable of moving between very different states. This makes our 5-hour world more interesting, because it was not one unchanging scene. The extremely rapid rotation probably belongs closest to the violent beginning when Earth and Moon had recently emerged from the giant impact period. As time continued, the surface cooled, crust formed, water condensed, impacts became less dominant, and the length of the day gradually increased. If we could watch the process over tens or hundreds of millions of years, we would not see a single young Earth, but a sequence of young Earths, each slightly different from the one before it. The sky would change as the moon moved outward. The ground would become more solid. The atmosphere would evolve. Oceans could appear and persist. The rotation would continue, slowing quietly through all of it. During the hottest stage, the sky above the magma would have been nothing like our clear modern atmosphere. Material heated during the impact could form vapour containing rock-forming substances as well as volatile compounds. As the planet cooled, different materials would condense at different temperatures. Water vapour, carbon-bearing gases, nitrogen-bearing compounds, and gases released through volcanic activity would contribute to an evolving atmosphere. We should be cautious about giving this atmosphere one permanent recipe, because early Earth's atmospheric composition changed and remains an active subject of research. What we can say safely is that it was not today's oxygen-rich air. Free molecular oxygen became abundant much later, after life had already existed for a very long time. A visitor attempting to take a refreshing breath on this world would have several problems to choose from before oxygen deficiency even reached the top of the list. Above all of this, the sky would appear to move quickly because the entire planet beneath it was rotating quickly. If the full day lasted around 5 hours, the sun's apparent daily path would be compressed into a small fraction of the time we are accustomed to. Near the equator and under a roughly even division of daylight and darkness, sunrise to sunset might occupy only a couple of hours. The exact duration would depend on latitude, orbital geometry, axial tilt, and the distinction between Earth's rotation relative to distant stars and the solar day measured from one noon to the next. But none of those details change the basic experience. The sun would not seem to linger in the sky. Morning, noon, evening, and night would follow one another with remarkable speed. Try comparing it with an ordinary modern morning. Suppose you wake at 7. On today's Earth, the sun may spend hours climbing before reaching its highest point. Breakfast ends, the morning continues, people go to work, and noon eventually arrives according to a very familiar rhythm. On a 5-hour Earth, one complete rotation could be nearly finished before a modern morning was over. Someone attempting to organise a day around sunrise might discover that by the time breakfast had been prepared, discussed, eaten, and followed by the usual question of who was going to wash up, afternoon was already becoming a historical event. The stars would seem to move just as quickly at night. On the modern Earth, constellations creep gradually across the sky. Their motion is easy to miss unless you watch for a long time or compare their positions over several hours. Under a 5-hour rotation, that movement would be obvious much sooner. A constellation rising near the eastern horizon would climb and cross a large part of the sky during the length of a modern film. The entire celestial sphere would appear to turn rapidly, even though most of the motion would actually be coming from Earth itself. Anyone who somehow arrived from the present would probably feel that the sky had been placed on fast forward. The moon would make the view much stranger. It formed close to Earth and has been moving outward ever since as tidal interactions transfer angular momentum from Earth's rotation into the moon's orbit. The present average Earth-Moon distance is about 384,000 kilometres, but the early moon was far closer. The exact distance immediately after formation depends strongly on the particular model used, so it is better not to imagine one precise giant moon hanging at a precisely known height. What matters is that a much closer moon would occupy a larger apparent area of the sky and produce much stronger tidal forces than it does today. The familiar small disk that now fits neatly behind a raised thumb would not have looked so modest. Its movement would also be different. The moon does not simply hang above one point on Earth. It orbits in the same general direction that Earth rotates, and the apparent motion seen from the surface depends on the relationship between those two motions. With Earth turning rapidly and the moon orbiting much closer than today, the timing of lunar rising, setting, and tidal cycles would differ greatly from modern experience. The early sky was therefore not merely a quicker version of our own. Both of its most obvious objects, the sun and moon, would follow unfamiliar schedules. Once water began collecting at the surface, the closer moon became particularly important. Strong lunar gravity would deform Earth much more than it does today. The resulting tides could be enormous compared with modern tides, although their actual height at any coastline would depend on the shapes and depths of the ocean basins, the arrangement of land, and the frequency with which tidal waves interacted with local geography. It is easy to say that an early closed moon meant giant tides, but the details are complicated. A tide several meters high in one basin and a much larger tide in another are both possible depending on resonance and coastal geometry. The safe conclusion is that tidal forcing itself was much stronger when the moon was closer. These tides would not resemble a single wall of water permanently sweeping around the planet. Even today, tides are waves and deformations moving through ocean basins under the influence of lunar and solar gravity. In the early Earth system, the much shorter day and closer moon would create different forcing periods. The oceans, once sufficiently established, would have had to respond to a rapidly changing gravitational pattern. Water would move, coastlines would experience repeated flooding and retreat, and energy would be dissipated through friction and turbulence. Every bit of that dissipation mattered because it contributed to the process that was slowing Earth's rotation. The atmosphere would also respond to fast rotation. Earth's present weather patterns are strongly influenced by the Coriolis effect, which appears because air and water move over a rotating spherical planet. Near the equator, the surface is moving eastward faster than regions closer to the poles. Air travelling north or south carries some of its original eastward motion with it, causing large-scale paths to curve relative to the surface. This contributes to the organisation of trade winds, jet streams, ocean currents, and rotating storms. Increase Earth's rotation rate dramatically, and rotational effects become more important over shorter distances. Climate models of rapidly rotating planets generally produce circulation patterns divided into narrower bands than those of slowly rotating planets. Instead of a few enormous circulation cells reaching across broad latitudes, a fast-spinning atmosphere can develop more strongly constrained jets and smaller-scale structures. That does not allow us to draw an exact weather map of 5-hour Earth, because the atmosphere itself was very different and changed considerably as the planet cooled. It does mean that the rapid rotation was not merely something visible in the movement of the sun, it influenced the motion of the atmosphere and oceans as well. A hurricane is a useful modern example of why rotation matters, although there were obviously no modern hurricanes over familiar oceans immediately after the moon-forming impact. Tropical cyclones gain their energy from warm ocean water, but Earth's rotation helps organise their circulation. If rotation were dramatically different, the scales and behaviour of large weather systems would also differ. On the young Earth, whenever stable oceans and a sufficiently thick atmosphere existed, weather would have operated within the rules created by a planet spinning several times faster than it does now. The result would not simply be stronger versions of today's storms, it could involve different circulation zones, wind patterns, and ways of transporting heat from equator to pole. Rapid rotation would even affect the shape of the planet beneath those winds. Modern Earth is slightly wider at the equator than from pole to pole because rotation produces an outward centrifugal effect. The difference today is modest. Earth's equatorial diameter is about 43 kilometers greater than its polar diameter. At a 5-hour rotation period, the equatorial bulge would have been substantially stronger. Exactly how much depends on Earth's internal structure at the time, including whether major portions were molten, because a fluid or partially fluid world can adjust its shape more readily than a rigid one. The result would be a young Earth that was somewhat more flattened at the poles and swollen around the equator. Gravity at the equator would also be affected by the faster rotation. The planet would still hold onto its surface and atmosphere. 5 hours is fast, but not fast enough for Earth to disintegrate. There is a rotation rate at which material near the equator could approach orbital conditions, but a 5-hour Earth remains safely on the side where gravity wins. So although the phrase Earth spinning 5 times faster Sounds as if everything should be flying outward into space. Our planet is far too massive for that particular disaster. The rapid spin could, however, influence molten material inside Earth. A young planet was differentiating, meaning dense substances such as iron were moving inward, while lighter silicate material remained higher in the mantle. Much of Earth's core formation happened very early, and the giant impact itself may have stirred and redistributed the interior. Rotation affects moving fluids, so the young planet's faster spin would have participated in the complicated convection, occurring inside molten or partially molten layers. Scientists reconstructing this period rely heavily on numerical simulations because essentially none of the original surface survives in an intact form. That lack of surviving surface is one reason the early Earth remains difficult to picture with certainty. Earth's crust is constantly recycled. Plate tectonics destroys old oceanic crust at subduction zones and creates new crust at spreading centres. Continents preserve much older material, but even they are repeatedly heated, fractured, buried, uplifted and eroded. Almost every ordinary rock from Earth's first few 100 million years has been altered or destroyed. The most famous survivors are tiny zircon crystals, some of them older than 4 billion years, preserved inside younger rocks in places such as the Jack Hills of Western Australia. These microscopic minerals contain chemical information about conditions that existed when they formed. Some of those zircon suggest that solid crust and liquid water appeared relatively early. That is important because it changes the traditional picture of the Hadean as a continuous inferno. Earth may have moved from a global magma ocean to a crusted planet with water at the surface on geologically short timescales, only to experience later disruptions from impacts and volcanism. A traveller jumping forward by a few million years at a time might encounter wildly different scenes. First, an intensely hot post-impact planet, later a cooling crust, later still areas of liquid water, then another major impact disturbing the surface again. Water itself came from more than one possible source. Some was likely incorporated into the material from which Earth formed, while additional volatile-rich material could have arrived through impacts from asteroids and other bodies. As the mantle released gases, water vapour entered the atmosphere. When temperatures became low enough, that vapour could condense. Rain falling onto hot rock may have evaporated again repeatedly, before stable oceans could remain. Eventually, however, evidence indicates that liquid water was present very early in Earth's history. NASA's recent educational overview of the early planet describes volcanically released water and gases contributing to the developing atmosphere and surface environment as the heavy bombardment declined. Imagine what rainfall might have meant during that transition. A thick atmosphere containing large quantities of water vapour begins cooling. Clouds form. Rain falls onto newly solidified volcanic crust. Steam rises where the surface remains hot. Water runs downhill through landscapes that may exist only temporarily before lava or impacts reshape them again. There are no plants to hold soil in place because there is no soil in the modern biological sense. There are no roots, forests, or grasslands. Chemical weathering begins working directly on exposed rock. If stable oceans developed while the day was still much shorter than ours, they would experience extremely rapid cycles of light and darkness. Sunlight would warm the surface for a brief period, night would follow, and then another sunrise would arrive. The short duration of each cycle could reduce how deeply temperatures changed between day and night, compared with a slowly rotating world, because the surface would have less time to heat under sunlight or cool in darkness before conditions reversed again. The exact effect would depend heavily on atmospheric thickness, cloud cover, ocean depth, and greenhouse gases, but fast rotation generally gives the surface less time to respond thermally during each individual day-night cycle. The sun itself was also weaker. Stellar evolution tells us that the young sun produced substantially less total energy than it does today. NASA describes solar output during the first billion years of Earth's history as roughly 70% of the modern value. Yet geological evidence shows that liquid water existed on the surface, creating the well-known faint young sun problem. greenhouse gases and other climate feedbacks are thought to have helped compensate for the weaker sunlight. For our imaginary observer, this means the early sky could combine several conditions that sound contradictory. The sun was dimmer overall, yet parts of the planet were extremely hot because Earth was still releasing energy from formation and impacts. Later, as the surface cooled, greenhouse warming could help keep water liquid despite weaker solar output. The moon was much closer, but Earth was rotating so quickly that the entire sky seemed restless. None of these features can be understood independently. The planet's climate, rotation, atmosphere, oceans, interior and satellite were developing together. The young sun may also have been more magnetically active despite being fainter in total brightness. Young stars commonly produce strong magnetic activity, flares, and energetic particle events. Research supported by NASA has explored how intense solar activity could have affected Earth's early atmosphere and magnetosphere. So a dimmer young sun did not necessarily mean a quieter sun. The amount of visible energy was lower, while energetic events could be more severe than those we normally experience today. Against that background, a 5-hour day starts to feel less like the strangest feature of the planet and more like one item on a very long list. Earth was spinning rapidly, but it was also cooling from catastrophic impacts, building a new atmosphere, forming a crust, collecting water, interacting with a nearby moon, and orbiting a younger sun. This was not yet the Earth of continents and blue oceans that appears in photographs from space. It was a planet in the middle of becoming one. There is another difference we often overlook because our view of Earth is dominated by life. Modern landscapes are covered with biological signals. Forests alter the atmosphere. Microorganisms transform soils and sediments. Coral reefs build geological structures. Plants change erosion. Oxygen produced by photosynthesis affects minerals across the surface. Even many familiar colours depend directly or indirectly on biology. Remove all of that, and the planet becomes visually unfamiliar before changing anything else. There was no green vegetation on the 5-hour Earth. There were no animals crossing beaches and no birds moving through the sky. Whether life had begun at the earliest point we are describing is unknown, and the immediate aftermath of the moon-forming impact almost certainly predates the evidence we have for life. The oldest widely accepted traces of biology come from much later than the moon-forming event, although exactly when life first appeared remains debated. It is therefore safest to picture this extremely early, fast-spinning Earth as lifeless, at least as far as we can presently demonstrate. That absence would make the world strangely quiet in one sense, and extremely noisy in another. There would be no animal calls, insects breaking branches, or human machinery. But geological processes could provide plenty of sound if we imagine an atmosphere capable of carrying it. Wind, thunder, impacts, cracking crust, erupting magma, waves, and the constant movement of water once oceans developed. A rocky planet does not need life to be active. The rapid succession of sunrises and sunsets would continue above everything. One rotation ends and another begins. The moon moves through its close orbit. Tides deform the planet. Friction converts organized motion into heat. Angular momentum shifts from Earth's spin into the moon's orbit. None of this requires anyone to observe it. The machinery operates automatically. That last point is particularly useful because it brings us closer to the real reason the sky was racing in the first place. The young Earth did not happen to spin quickly because early planets generally preferred short days. Its rotation had been produced by a history of collisions, and the final speed depended on the direction and force with which material arrived. The moon-forming impact then altered the system on a planetary scale. To understand why a world as large as Earth could end up turning once every few hours, we have to look more carefully at angular momentum, at how planets acquire spin while they form, and at what happens when one nearly finished world collides with another. That collision did more than create a nearby moon and leave Earth glowing with heat. It helps set the starting speed of the planet, whose rotation the Moon would spend the next several billion years slowing down. The reason the young Earth could rotate once in only a few hours begins with something that sounds simple, but becomes surprisingly complicated when the object involved is an entire planet. Earth spins because the material that formed it was already moving. Long before there was a solid surface, an ocean or a moon, the young solar system was filled with matter orbiting the Sun. Dust, rock, metal and larger bodies were all travelling through space, colliding with one another and gradually building the planets. None of those collisions happened in perfectly neat straight lines. Objects usually struck at an angle, and angle collisions could make the growing Earth rotate faster, slower, or in a different direction. By the time Earth had become a substantial world, its spin was already the accumulated result of an enormous number of impacts. The particularly dramatic part came near the end of that construction process, when another large planetary body collided with Earth and helped establish the rapidly rotating Earth-Moon system we're interested in tonight. Simulations of late-stage planetary formation have found that giant impacts can leave merged planets rotating with periods shorter than 5 hours, showing that very rapid rotation is a natural possible outcome of these enormous collisions. To understand why, it helps to begin with angular momentum. The name sounds technical, but the basic idea is familiar. Anything that rotates carries angular momentum, and once that rotational motion exists, it does not simply disappear without being transferred somewhere else. A spinning office chair is a small example. Sit on one with your arms extended and begin turning, then pull your arms toward your body. You rotate faster, extend them again, and you slow down. Figure skaters use the same principle when they pull their arms inward during a spin. Nothing mysterious has been added to the system. The distribution of mass has changed, and the rotation adjusts while angular momentum is conserved. A planet follows the same physics, although it is considerably less cooperative about fitting into an ice rink. The material that became Earth was orbiting the Sun, so it already possessed motion before Earth existed as a single object. As pieces collided and merged, some of their orbital motion became part of the growing planet's rotation. Imagine two large bodies approaching one another. If they meet perfectly centre to centre, their collision does not necessarily create much spin. But if one strikes the other off centre, the impact delivers a turning effect. It is similar to pushing a door near the hinge compared with pushing near the handle. The same push applied farther from the pivot produces a much greater tendency to rotate the door. Planetary impacts work according to the same basic principle. The difference is that the door is thousands of kilometers wide. The object pushing it may be the size of a small planet, and the entire event happens at speeds measured in kilometers per second. Early Earth experienced many such collisions while it was growing. Some would have arrived from one direction, others from another, so the final rotation was not simply the result of one continuous push. The planet's spin evolved as its mass increased. A collision might add angular momentum in the same direction Earth was already rotating and speed it up. Another could arrive from an opposing direction and reduce that rotation. A sufficiently large impact could even change the orientation of the planet's spin axis. This chaotic process helps explain why the planets in our solar system do not all rotate in the same way. Venus rotates extremely slowly, and in the opposite sense from most planets. Uranus is tilted so dramatically that it appears to rotate almost on its side. Jupiter spins rapidly. Mars and Earth happen to have similar present-day day lengths, but that similarity is not evidence of a universal planetary timetable. Each world carries a record of its own formation history in the way it rotates. Earth's most important rotational event appears to have involved the object usually called Theia. The standard giant impact picture proposes that a body roughly comparable in size to Mars struck the young Earth during the first part of solar system history. NASA's current overview describes the Moon as the product of an enormous early collision, while also noting that scientists continue to test different versions of the event, including models involving different impact energies, geometries, and ways of placing material into orbit. The precise reconstruction is still debated because the collision happened more than 4.4 billion years ago, and Earth's later geological activity erased almost all direct surface evidence. The basic connection between a major collision and lunar formation, however, remains the leading framework for explaining the Earth-Moon system. Theia was not simply a large asteroid. A Mars-sized body is a world in its own right. Mars has a diameter of nearly 6,800 kilometers, so imagining an object of comparable scale approaching the proto-Earth takes us far outside anything humans have ever witnessed. The two bodies would have been moving under their mutual gravity before impact, accelerating as they approached. When they finally met, the collision released an extraordinary amount of energy. Rock did not behave like brittle stone from a garden wall. Under those pressures and temperatures, huge quantities of material melted and vaporized. The shapes of both bodies changed within a short period, and material from Earth and the impactor could be launched into orbit. Some recent high-resolution simulations even suggest that a moon-like body could have been placed into orbit surprisingly quickly, rather than requiring all lunar material to remain as a diffuse debris disk for a long period. That is one example of how the details continue to evolve as simulations improve. The direction of the collision mattered enormously. If Theia had struck Earth directly through the centre, much of the rotational outcome would have been different. The classic giant impact models instead involve an off-centre collision, because that provides the angular momentum required both to spin Earth rapidly and to place substantial material into orbit rather than simply merging everything into one body. Researchers have long used the present angular momentum of Earth's rotation, combined with the Moon's orbit, as one of the major constraints on impact models. Whatever happened billions of years ago has to produce a system that can eventually evolve into the one we observe today. A model that creates a moon with the right mass but gives the system completely wrong rotational motion is not enough. A successful explanation has to account for several things at once: Earth's spin, the moon's orbit, the moon's relatively small iron core, the chemical similarities between Earth and lunar rocks, and the later tidal evolution of the system. This is where a 5-hour day becomes much more than an entertaining number. It is connected to the angular momentum stored in the early Earth-Moon system. Today, a large portion of that angular momentum is associated with the Moon's orbit around Earth, while Earth itself rotates once every 24 hours. Earlier in the system's history, the Moon was much closer, and Earth was spinning much faster. NASA scientists discussing the early Earth-Moon relationship have described the young Earth as having a day of roughly 5 hours, with the Moon later moving outward as tides slowed Earth's rotation. Another NASA explanation of lunar formation notes that the present spin of Earth and orbital motion of the Moon can be used together to infer that the Earth must have rotated much more rapidly when the Moon formed close by. It may help to imagine the difference without thinking about clocks at all. Take modern Earth and place a marker on the equator. As Earth rotates once in roughly 24 hours, that marker travels all the way around the planet. Now make the same rotation happen in about 5 hours. The marker must cover approximately the same circumference in less than 1/4 of the time. Everything associated with Earth's rotation speeds up accordingly. The surface at the equator moves much faster. The apparent motion of the Sun becomes much quicker. The centrifugal effect associated with rotation becomes stronger. The planet develops a more pronounced equatorial bulge. None of this requires an engine inside Earth actively making it turn. The spin is simply leftover motion from the way the planet was assembled and struck. The easiest mistake is to imagine that once the giant impact finished, Earth should naturally have slowed itself down simply because rotating that quickly seems excessive. But rotation does not disappear, because it looks inconvenient. In empty space, there is very little external resistance. A spinning world can continue rotating for an extremely long time unless some interaction transfers its angular momentum elsewhere. There is no cosmic brake pad rubbing against the equator. Space is not thick enough to provide the kind of drag that slows a bicycle wheel. Something else had to interact gravitationally with Earth, Unfortunately for the history we're discussing, the giant impact had just produced a very large object capable of doing exactly that. Before reaching that slowdown, though, it is worth staying with the impact itself for a little longer, because there was probably no single clean moment when one version of Earth ended and another began. Immediately after the collision, the planet could have been heavily distorted and partly vaporized. Some simulations of very energetic impacts produce a temporary structure, sometimes described as a synestia, a hot, rapidly rotating mass of vaporized and molten rock whose outer portions extend beyond the shape of an ordinary planet. Not every lunar formation model requires Earth to have entered this exact state, and scientists continue debating which impact conditions best explain lunar composition. The broader lesson is more secure. When two planetary bodies collide, the immediate result does not have to resemble a neat sphere with a clearly defined surface. For some period, the distinction between planet, atmosphere, magma, vapor, and orbiting material could have been much less tidy than it is today. As energy escaped into space, the post-impact structure cooled. Vapor condensed, molten material collected. Dense iron tended to move inward while lower density silicates remained outside. Orbiting material either fell back to Earth, escaped, or contributed to the Moon. In the classic picture, debris gathered into a disk before accreting into the Moon. Newer simulations show that some material could potentially have assembled into a large satellite much faster. Either way, by the time a recognizable Earth and Moon emerged, they were far closer together than they are today, and Earth carried a large amount of rotational angular momentum. NASA's lunar science material emphasizes that any viable formation model has to reproduce both the Moon's position and the rotational orbital state of the system after billions of years of tidal evolution. There is an interesting consequence of forming a planet through many random impacts. Earth did not have to rotate in the direction it does now. The fact that the Sun rises in the east is a result of Earth's present prograde rotation, but planetary formation could have produced other outcomes. Numerical studies of giant impacts show a broad range of possible spin axis orientations, including planets rotating in directions very different from their orbital motion. Earth's eventual orientation is therefore not something that had to happen. We live with one surviving result from a chaotic period containing many possible outcomes. The angle of Earth's axis may also have been affected by the Moon-forming collision. Our planet currently rotates with an axial tilt of about 23.4 degrees relative to its orbit, producing the seasons as first one hemisphere and then the other receives more direct sunlight. Reconstructing the exact early tilt is difficult because gravitational interactions later change the Earth-Moon system, and different giant impact models can begin with different orientations. It would be too simple to say that Theia struck Earth and instantly set today's exact tilt. What the impact certainly could do was deliver enough angular momentum to alter the orientation of the young planet dramatically. Once again, the familiar geometry of modern Earth was not necessarily present from the beginning. The amount of angular momentum delivered depends partly on impact speed, angle, and the masses involved. An impactor approaching nearly head-on provides a different rotational result from one that barely clips the edge. A relatively slow grazing collision can merge material while preserving substantial rotational motion. A faster event can vaporize more material and potentially eject more mass. Scientists run numerical simulations across large ranges of these parameters and then compare the results with observations of Earth and Moon. It is less like replaying a known recording and more like working backward from the scene left behind. We know the masses of Earth and Moon. We know their compositions reasonably well. We know their present orbit and spin. We know the Moon is unusually large compared with Earth when measured against many other planet-moon systems. The task is to identify which ancient collision histories could naturally lead to all of those properties. The Moon's chemistry makes the problem particularly interesting. Apollo astronauts returned hundreds of kilograms of lunar material, allowing researchers to compare Moon rocks directly with terrestrial rocks. The two bodies share remarkably similar isotopic characteristics for several elements. which suggests a close relationship between the material from which they formed. At the same time, the Moon is relatively poor in iron compared with Earth, and depleted in various volatile elements. A successful moon formation model has to explain why material from a giant impact would produce those similarities and differences. NASA notes that evidence from lunar samples supports a high-energy origin involving widespread melting, while the Moon's small iron core fits the idea that much of the metal in the colliding bodies ended up in Earth, rather than in the orbiting material that formed the Moon. This is why scientists have developed multiple versions of the giant impact idea, rather than treating the earliest model as permanently settled. Some scenarios use a Mars-sized Theia striking a nearly completed Earth. Others explore higher energy impacts, different mass ratios, rapidly spinning proto-Earths, or multiple collisions. Each version attempts to solve particular problems while respecting the basic physical constraints. Current reviews still describe the giant impact framework as the dominant explanation, while emphasizing that questions about the precise impact geometry, the source of lunar material, and the system's initial angular momentum remain active research topics. For our purpose, though, those uncertainties do not erase the main reason Earth was spinning so quickly. Planet formation created rotation through collisions, and a final giant collision supplied or redistributed a very large amount of angular momentum. The newly formed Earth-Moon system therefore began in a much more compact and rapidly rotating state than the system we see now. There is no need to invent some temporary force that made the young planet spin quickly. Fast rotation is exactly the kind of outcome that can emerge when planetary bodies collide off-center during formation. You can see the same principle in smaller events. Suppose two lumps of clay collide directly and stick together. The combined lump may move forward but rotate only slightly. Now imagine one lump striking the outer edge of the other. The combined mass begins turning. Increase the speed, increase the masses, remove the table, place the experiment in orbit around a star and give gravity several million years to collect the debris, and the simple classroom picture begins to resemble the physics of planetary formation. The mathematics becomes much more complicated, but the underlying idea remains familiar. Another reason the early Earth could maintain such a short day is that its mass was concentrated relatively close to its rotation axis, compared with the later Earth-Moon system taken as a whole. Once a significant amount of angular momentum was transferred outward into the Moon's increasingly distant orbit, Earth's own rotation slowed. The figure skater comparison works surprisingly well here. A skater spins faster when mass is held closer to the axis, and slower when mass is extended farther outward. Earth and Moon are not physically connected like a skater's arms, so the mechanism is different, but the conservation principle is related. Through tides, angular momentum moved from Earth's spin into the Moon's orbit, and that orbital angular momentum was associated with a Moon gradually moving farther away. NASA scientists have used essentially this comparison when explaining why the close early Earth-Moon system involved a much faster spinning Earth. There is a useful detail hiding inside that explanation. The Moon did not steal Earth's rotation all at once. The transfer required an ongoing gravitational interaction, and it could continue because Earth rotated faster than the Moon orbited. The tidal bulges raised on Earth were carried ahead of the line connecting Earth and Moon. The Moon's gravity pulled backward on those bulges, slightly slowing Earth's rotation. The bulges in turn pulled forward on the Moon, increasing its orbital energy and angular momentum. The Moon moved outward and Earth slowed down. Every step was tiny compared with the size of the system, but the process continued for billions of years. Run the same process backward in your imagination, and you see why the 5-hour day makes sense. Remove angular momentum from the Moon's distant orbit and return it to Earth's spin. Bring the Moon progressively closer, Earth's day becomes shorter. Continue far enough and the 24-hour day disappears entirely. The planet turns once in 15 hours, then 10, then perhaps only several hours as we approach the period of lunar formation. The modern world has not always been slowing from some arbitrary fast rotation. Its present day length is part of a continuous exchange occurring within the Earth-Moon system. There were limits, of course. Earth could not spin arbitrarily fast while remaining an ordinary planet. Increase the rotation enough, and the centrifugal effect at the equator eventually competes seriously with gravity. Material could become unstable or even be lost. A 5-hour day is very fast by modern terrestrial standards, but not fast enough to tear Earth apart. Giant impact simulations can produce rotation periods of this order, while still leaving a gravitationally bound planet. The young Earth would be noticeably more oblate, with a larger equatorial bulge, but it would remain a planet rather than becoming a spray of rocks every few hours. The internal state of Earth also mattered. A hot, partly molten planet can adjust its shape more readily to rapid rotation than a cold, rigid body. After the moon-forming impact, Earth was extremely hot, so its outer layers could respond efficiently to the combination of gravity and rotation. The equilibrium shape of such a body would naturally become flattened along the rotational axis and expanded around the equator. As Earth cooled and its rotation slowed, that rotational distortion became less extreme. Even now, the planet retains a measurable equatorial bulge because 24 hours is still fast enough for rotation to affect its shape. This makes the young Earth's 5-hour day a direct physical link between the violence of planetary formation and something as ordinary as the passage from morning to evening. The reason our distant planet experienced such brief days was not that time itself was moving differently. A second would still be a second according to the same underlying physics. The difference was mechanical. Earth was turning much faster. The sun appeared to cross the sky quickly because our entire world was completing rotations at a rate inherited from its formation and giant collisions. And although the giant impact gave Earth an extraordinary rotational state, it also produced the object that would gradually undo much of it. The Moon's creation and Earth's rapid spin were not separate episodes. They were two results of the same event. The collision left a fast-rotating Earth surrounded by material that became a close-orbiting Moon, and from that point onward the gravitational relationship between the two began changing both worlds. The Moon did not remain where it formed. Earth did not keep its 5-hour day. Their early closeness made the tidal interaction far stronger than it is now, and that means the next part of the story requires us to bring the Moon much nearer than the small familiar disk we see tonight, and ask what the sky, the tides, and the surface of Earth would be like with a large lunar companion orbiting close overhead. If the young Earth already seems unfamiliar because it was completing a rotation in only a few hours, the Moon makes the picture stranger still. Today, the Moon feels distant in every sense of the word. It hangs quietly in the sky, small enough to cover with a fingertip, and on an ordinary night it can be surprisingly easy to ignore. Its average distance from Earth is about 384,400 kilometers, or roughly 238,855 miles. That gap is so large that around 30 Earth-sized planets could be placed side by side between Earth and the Moon. Yet the Moon didn't begin its history anywhere near that far away. It formed much closer to Earth, and the distance between the two worlds has been increasing ever since. Laser measurements made using reflectors left on the Moon show that this movement continues today at about 4 centimeters, or around 1.5 inches each year. That does not sound impressive until you remember that the process has been operating for billions of years. The Moon's original closeness is not an optional detail added to make early Earth more dramatic. It follows directly from the way the Earth-Moon system evolved. The Moon formed after the enormous collision we have already discussed, when material thrown from the young Earth and the impactor collected into a satellite. Whatever the exact details of that event, any successful model has to produce a Moon that begins much nearer Earth than it is today, and then moves outward as the system exchanges angular momentum. NASA's current overview of lunar formation specifically notes that the Moon's continuing recession tells us it must initially have formed much closer to Earth, while Earth's rotation at the time was much faster. One NASA model of the early Earth-Moon environment places the Moon at about 80,000 miles from Earth around 4 billion years ago, compared with roughly 238,000 miles today. That would make it approximately 3 times closer than it is now. Earlier still, nearer the time of formation, the Moon would have been closer again, although assigning one exact distance to the immediate post-impact Moon is difficult, because different formation models produce somewhat different initial conditions. The important point is that an observer on ancient Earth would not have looked up and seen the modest Moon we know. The Moon would have occupied a much larger portion of the sky, and would have exerted a much stronger gravitational influence on Earth. At around 1/3 of its present distance, the Moon would appear roughly 3 times wider in the sky than it does now. That estimate is only approximate because the Moon's orbit is not perfectly circular, and the ancient distance changed continuously, but it gives a useful sense of scale. The modern full Moon is about 1/2 degree wide as seen from Earth. Make the Moon several times closer without changing its physical diameter, and its apparent size becomes several times larger. Instead of a small bright disk that people occasionally mistake for being larger near the horizon, the early Moon would have been an unmistakably large object whenever it was visible. It is worth being careful with the mental picture, though. The Moon would not have looked like the enormous fictional object sometimes shown filling half the sky in films. Even at a fraction of its present distance, it would still be an astronomical body seen from tens of thousands of miles away. It would simply look much larger than the Moon you know today. If you somehow transported a modern observer to that period and allowed them to ignore the lack of breathable air, unfamiliar landscape, intense geological activity, and every other practical problem, the Moon would probably be one of the first things they noticed. It would immediately tell them that something about the Earth-Moon system was very different. The Moon would also move across the sky differently. Today, it takes about 27.3 days to complete one orbit around Earth relative to the distant stars. Its phases repeat approximately every 29.5 days, because Earth itself is moving around the Sun at the same time. The early Moon, being closer to Earth, travelled around our planet much more quickly. Kepler's laws tell us that an object in a smaller orbit generally has a shorter orbital period, so the ancient lunar month was not the month we know today. The Moon would cycle through its orbital positions more rapidly, while Earth itself was rotating much faster beneath it. The combined result would create a sky whose daily and monthly rhythms were both compressed compared with modern experience. This is where trying to imagine an ordinary ancient night becomes difficult. On modern Earth, you can watch the Moon rise in the east and gradually cross the sky over many hours. Its position against the stars changes from night to night, but the movement is usually too slow to notice over a few minutes. On the very young Earth, the ground beneath the observer could complete a full rotation in roughly 5 hours, while the Moon itself followed a much tighter orbit. The Moon would still rise and set because Earth was rotating beneath it, but the timing would be unlike anything we experience now. It would not simply be today's Moon played at higher speed. The Moon's own orbital motion would be substantially faster as well. The lunar phases would still exist because phases are created by the changing geometry between the Sun, Earth and Moon. A full moon occurs when the hemisphere facing Earth is illuminated almost completely by the Sun, while a new moon occurs when the Moon is positioned roughly between Earth and the Sun, and the illuminated side faces mostly away from us. That geometry does not require a 29.5-day month. Put the Moon into a closer, faster orbit, and the phase cycle becomes shorter, so the early sky could pass from one lunar configuration to another on a schedule that would seem unusually hurried to us. The Moon may also have reached tidal locking fairly early in its history. Today, the Moon rotates on its axis once during each orbit around Earth, which is why almost the same hemisphere always faces us. This is not a coincidence. Earth's gravity raised tides in the Moon itself. Those distortions dissipated energy inside the young Moon and gradually altered its rotation until its spin synchronized with its orbit. Once that happened, one side remained directed toward Earth. NASA describes tidal locking as a natural consequence of this energy loss. with the moon's rotation settling into synchronization with its orbit, while the satellite continues gradually moving outward. That means an observer on early Earth may eventually have seen a familiar feature despite all the differences, essentially the same lunar hemisphere turning toward Earth. The details of the surface would not have looked exactly like the moon we see now because the moon itself was young. Its crust, volcanic history and bombardment record were still developing. Many of the large dark plains that dominate today's near side had not yet formed in their modern appearance. Enormous impacts would later excavate basins, and volcanic lava would later fill some of them. So although the moon may have become tidally locked, its face was still changing. The moon's own interior was much hotter in the beginning. It formed from material involved in a giant collision, and much of it was initially molten. Scientists describe an early lunar magma ocean, in which minerals crystallized as the moon cooled. Dense minerals tended to sink while lighter minerals, particularly Pleioklus feldspar, floated upward and contributed to the formation of the early lunar crust. Over time, the moon differentiated into a crust, mantle, and relatively small metallic core. The object hanging close above early Earth was therefore not merely a modern moon placed nearer to us. It was a geologically young moon still cooling from its own creation. Earth's gravitational influence on that moon would have been intense. Tides work both ways. We usually think about the moon pulling on Earth's oceans because that is what produces the familiar rise and fall of sea level along our coastlines. But Earth also raises tides on the moon. Even today, Earth's gravity slightly deforms the solid lunar body. NASA measurements indicate that the modern lunar body tide can raise a deformation of roughly half a metre. When the moon was much closer, Earth's tidal influence on it was far stronger. The same was true in the opposite direction. A closer moon meant stronger lunar tides on Earth. This happens because tidal force depends not simply on the moon's gravitational pull, but on the difference in that pull across Earth. The side of Earth nearest the moon feels a slightly stronger attraction than Earth's centre, while the far side feels a slightly weaker one. The difference stretches the planet along the Earth-Moon direction. Water responds very easily, creating ocean tides, but solid rock responds as well. Modern Earth itself flexes under lunar gravity. On the early Earth, with the moon much nearer, that deformation could have been far more significant. Distance is particularly important because tidal effects weaken extremely quickly as two objects move apart. Roughly speaking, the tide-producing influence changes with the inverse cube of distance. So moving the moon to 1/3 of its present distance does not merely make its tidal influence 3 times stronger. Under a simple comparison, it could make the tide-generating effect around 27 times stronger. The real tides that appear in oceans are more complicated because ocean depth, basin shape, coastlines, resonance, and Earth's rotation all affect how water responds. But the underlying gravitational forcing from a nearby moon would be dramatically greater. This is why it is misleading to imagine the early moon only as an impressive object in the sky. Its most important effects were happening throughout Earth. The moon pulled on the planet constantly. Earth rotated beneath the tidal distortion. Rock flexed. Later, oceans moved. Friction and turbulence converted some of that organised motion into heat. That energy had to come from somewhere, and a large portion of it came from Earth's rotation. The process is easier to see by starting with modern tides. The moon's gravity produces 2 broad tidal bulges, one generally on the side of Earth facing the moon, and another on the opposite side. Earth is rotating much faster than the moon goes around Earth, so the rotation carries those bulges slightly ahead of the exact Earth-Moon line. The moon then pulls backward on the displaced bulges. That gravitational pull creates a torque that slows Earth's rotation. At the same time, the bulges pull forward on the moon, adding angular momentum to its orbit and pushing it farther away. NASA describes this ongoing exchange as the reason Earth's rotation gradually slows while the moon's orbit expands. On the early Earth, the same basic relationship was operating under much more extreme conditions. Earth was spinning faster, the Moon was much closer, and tidal deformation was much stronger. That meant the interaction could transfer angular momentum far more efficiently than it does today. The 5-hour day was therefore already being modified almost as soon as the Earth-Moon system existed in a recognisable form. There was no long period during which Earth politely maintained a 5-hour rotation before the Moon eventually decided to interfere. The closed Moon and the rapidly spinning Earth were interacting from the beginning. The Moon's outward movement was the other side of Earth's slowdown. It is tempting to imagine that the Moon is simply drifting away because Earth's gravity is becoming weaker, or because the Moon is somehow escaping. Neither is correct. Earth still holds the Moon gravitationally, and the Moon remains securely in orbit. The increasing distance results mainly from angular momentum being transferred from Earth's rotation into the Moon's orbital motion. As the Moon gains orbital angular momentum, its orbit becomes larger. Counterintuitively, a satellite in a larger orbit actually travels more slowly around its planet, even though it has gained orbital energy. So as the Moon moved outward, the lunar month became longer. This means that two different clocks were changing together. Earth's rotation slowed, so the day became longer. The Moon moved outward and took longer to orbit Earth, so the lunar month became longer as well. The relationship between those cycles also changed. On the earliest Earth, days were extremely short and lunar orbits were much shorter than today's month. Billions of years later, one Earth rotation takes 24 hours, while the Moon requires more than 27 days to complete an orbit relative to the stars. Both numbers are products of the same ongoing gravitational evolution. We know that the Moon is still moving outward because humans have measured the distance with extraordinary precision. Apollo astronauts placed retroreflectors on the lunar surface, and additional reflectors were later delivered by Soviet robotic missions. Observatories on Earth can fire laser pulses toward these reflectors and measure how long the light takes to return. Since the speed of light is known extremely accurately, the travel time gives scientists a precise measurement of the Earth-Moon distance. Repeating the measurements over decades has revealed the average recession of about 3.8 to 4 centimeters per year. If that current rate was simply multiplied backward for billions of years, however, we would run into trouble. The recession rate has not remained constant. Tidal dissipation depends strongly on Earth's oceans and continents. Modern tides interact with particular ocean basins whose shapes can amplify or weaken tidal motion. Continents block and redirect tidal waves. Shallow continental shelves dissipate substantial energy. In earlier geological periods, the continents occupied completely different positions. Ocean depths were different, and during the very earliest Earth, the oceans themselves were still forming. So the efficiency with which Earth transferred rotational energy to the Moon changed over time. This is an important correction because a simple calculation using today's recession rate can produce a misleading history. Scientists reconstruct the Moon's orbital evolution using dynamical models together with geological evidence for ancient tides and day lengths. Some sedimentary rocks preserve repeated layers associated with tidal cycles, producing what are sometimes called tidal rhythmites. By counting and comparing those patterns, researchers can estimate how many daily tidal cycles occurred within longer lunar or seasonal cycles. Other geological and biological records can also preserve information about Earth's ancient rotation. These records show that the lengthening of the day and outward movement of the Moon have not proceeded at one perfectly constant rate. The arrangement of continents can make a remarkable difference. Modern Earth has an Atlantic Ocean with dimensions that allow strong tidal responses in certain regions. Some coastlines funnel water and create unusually large local tides. The Bay of Fundy in Canada is a familiar modern example where the shape and natural oscillation of the basin help produce an enormous tidal range. Ancient Earth had different basins with different resonances. A strong astronomical tidal force does not automatically translate into one universal height of water everywhere. Local geography determines how that force is expressed at the coast. This becomes even more important when thinking about the early moon. It is common to hear descriptions of ancient tides hundreds or even thousands of meters high sweeping repeatedly around Earth. Such claims should be treated cautiously. A much closer moon certainly produced stronger tidal forcing, but the actual height of a tide at a particular place depends on the structure of the oceans and land available at that time. Immediately after lunar formation, when Earth's surface may still have been largely molten, there may not even have been ordinary oceans in which familiar tides could operate. Later, once extensive liquid water existed, the geography was still completely unlike the modern world. What we can say with much greater confidence is that Earth itself was being strongly deformed. The moon's gravity does not require an ocean in order to raise a tide. Molten rock, a partially molten mantle, solid crust, atmosphere, and eventually oceans can all respond in different ways. The young Earth's body tide could dissipate energy internally, while later oceans provided an extremely effective additional mechanism for tidal friction. The closer the moon was, the stronger that gravitational cycling became. The moon also influenced Earth's orientation in space. A large satellite can affect the long-term behaviour of a planet's rotational axis. NASA researchers studying the early Earth-Moon system have discussed the moon's role in stabilising Earth's spin axis. Although the exact history of Earth's obliquity during the earlier stages is complicated, the modern moon is unusually large relative to its planet compared with many other satellites in the solar system, and that close partnership has affected Earth's rotational evolution in ways that a small distant moon would not. Another effect would have been more obvious to an observer: eclipses. The modern moon happens to have almost the same apparent diameter in the sky as the sun, which allows total solar eclipses to occur when the moon passes directly between Earth and the sun. A much closer moon would look substantially larger than the sun. When the orbital alignment was correct, a solar eclipse could therefore cover the sun with room to spare. The region of totality and exact duration would depend on the moon's distance, orbital geometry, Earth's rotation, and the observer's location, but the visual balance would not resemble the delicate fit we experience today. Modern total solar eclipses are possible during a particular period of Earth-Moon history, because the moon's apparent size is slowly decreasing as it recedes. Far in the future, assuming the Earth-Moon system survives long enough, the moon will appear too small to cover the sun completely, and total solar eclipses of the current type will cease. In the deep past, the opposite was true. The moon was larger in our sky, so it could cover the solar disk more completely. The famous near match between the apparent sizes of the sun and moon is therefore temporary, rather than a permanent feature of the solar system. Lunar eclipses would also occur under different geometry. A lunar eclipse happens when the moon passes through Earth's shadow. A closer lunar orbit changes the size of Earth's shadow at the moon's location and changes the moon's orbital speed, so eclipse timing would differ from what we know. Again, none of this required anyone to observe it. Long before eyes existed, the sun, Earth, and moon were repeatedly lining up and casting shadows across one another. The early moon itself would have experienced Earth as an enormous presence in its sky. From the modern moon, Earth already appears about 4 times wider than the moon appears from Earth, because Earth is much larger physically. For a tidally locked moon, Earth remains in roughly the same part of the sky from most places on the lunar near side rather than rising and setting every day. When the moon was closer, Earth would appear even larger. An observer on the early lunar near side, if such an observer could somehow exist, would see an enormous young Earth hanging almost permanently above the horizon or overhead depending on location, turning rapidly beneath its clouds, vapour, molten regions and later oceans. There is something useful about switching perspective in this way because it shows that neither world was passive. Earth raised tides in the moon and altered its rotation. The moon raised tides in Earth and altered Earth's rotation. Both objects changed shape under the other's gravity. Both evolved internally while their orbit evolved externally. The early Earth-Moon system behaved less like a planet with a decorative satellite and more like two gravitationally connected worlds continually exchanging energy and angular momentum. That exchange gradually reduced the extremity of the early system. The Moon moved farther away, so tidal forces weakened. Earth's rotation slowed, so the day lengthened. The Moon's orbit expanded, so its month lengthened. The immediate post-impact world became a cooler planet with more stable crust and eventually long-lived oceans. By 4 billion years ago, the Moon was already substantially farther out than it had been immediately after formation, even though one NASA estimate still places it only around 80,000 miles away, roughly 1/3 of today's distance. From there, the process continued through the entire history of life. The first microorganisms appeared under a closer moon than the one above us now. Complex cells evolved under shorter days. Animals entered the oceans while Earth was rotating faster than it does today. Dinosaurs lived with days somewhat shorter than ours, and a moon somewhat nearer. Every generation inherited a planet whose rotation was almost indistinguishable from that experienced by the generation before. Yet over geological time, the cumulative difference became measurable. The Moon we see tonight is therefore not sitting in the place where it began. Its current distance is the result of billions of years of interaction with Earth. Every centimetre of its gradual recession is connected to a tiny loss of Earth's rotational energy. The 5-hour world and the 24-hour world are two stages of the same process, linked by countless tides. And those tides are where the closed moon stops being mainly an object in the sky and starts becoming one of the most powerful agents shaping the daily behaviour of the young planet. Once extensive oceans existed, the rapidly rotating Earth and nearby moon created tidal conditions unlike anything along a modern coastline. Water was forced to respond to a stronger lunar pull, while the surface beneath it raced around the planet every few hours. Coastlines, ocean depths and continental arrangements changed the details, but the basic system had far more tidal energy available than it does now. Understanding what happened to that energy takes us down from the oversized moon in the sky and directly into the restless oceans below. Once the early moon is moved closer to Earth, the oceans become impossible to ignore. A nearby moon did much more than look larger in the sky. Its gravity acted more strongly across Earth, producing tides far more energetic than the ones we experience today. At the same time, Earth itself was rotating much faster, so the surface was carrying oceans through the changing Earth-Moon geometry at a much quicker pace. The result was a world where water, once long-lived oceans had formed, was being pushed, pulled, redirected and mixed under conditions that would look very unfamiliar to anyone standing beside a modern coastline. It is tempting to imagine towering walls of water racing continuously around the planet, but the real physics is more complicated than that. Ancient tides could certainly have been much stronger, yet their exact height depended on the depth and shape of the ocean basins, the arrangement of early land, the distance of the moon, and the rate at which Earth was rotating. What we can say with confidence is that far more tidal energy was available, and that energy had to go somewhere. Modern tides provide a useful starting point because the basic mechanism has not changed. The moon's gravity pulls more strongly on the side of Earth nearest to it than on Earth's centre, and it pulls slightly less strongly on the side farthest away. That difference stretches Earth along the line pointing toward the moon. Water responds by shifting across the surface, while the solid planet itself flexes slightly as well. The sun adds its own tidal influence, sometimes strengthening lunar tides, and sometimes partially opposing them depending on the relative positions of the sun, Earth and moon. What appears at a particular coastline is therefore the result of a global gravitational forcing interacting with local geography. Some places experience large tidal ranges, while others experience surprisingly small ones, even though they are on the same planet. Early Earth would have taken that basic system and turned several of its controls much higher. The moon was closer, which increased the tide-producing difference in its gravitational pull across the planet. Earth was rotating quickly, which changed how often regions of the surface moved through the tidal pattern. The continents, if recognizable continental masses had developed at the stage we were imagining, were nothing like those of today. Ocean basins were different, coastlines were different, and much of the crust was still evolving. Even the amount of water exposed at the surface may have changed through time. There was no Atlantic, no Pacific in its modern form, no Mediterranean, and certainly no harbour master calmly checking a printed tide table. The strength of a tidal force changes very rapidly with distance. Move the moon closer, and the increase is much greater than a simple one-to-one comparison might suggest. This is why the moon's early proximity mattered so much. A moon several times closer could generate a tide-producing force tens of times stronger than the modern one. That does not mean every ancient beach automatically experienced a tide tens of times higher than today's. Ocean water does not simply rise according to one universal formula. The shape of the basin determines whether water can move freely, become trapped, resonate, or lose energy through friction. Still, the gravitational driver was stronger, and that gave the young oceans far more energy to work with. Imagine a broad, early ocean basin with shallow margins. As the tidal deformation moved through it, enormous volumes of water could be forced back and forth across those shallow regions. Friction along the seafloor would remove energy from the moving water. Waves and currents would break against irregular coastlines. Narrow channels could accelerate the flow. Shelves could repeatedly flood and drain. Where the natural period of an ocean basin happened to match the tidal forcing particularly well, the response could become amplified. In another basin with a less favourable shape, the tides might be more moderate. This is exactly why modern tides can be dramatically different from one coast to another, except the ancient system began with a stronger gravitational influence. A 5-hour day would also change the frequency of the tidal cycle. Today, many coastlines experience roughly 2 high tides and 2 low tides during a little more than 24 hours, though local tidal patterns vary. The familiar interval is connected to Earth's rotation beneath the moon and the moon's own movement around Earth. On the rapidly rotating young Earth, the surface would pass through the tidal pattern much more quickly. High and low water could therefore alternate on a much shorter schedule. A coastline might experience substantial movement of water many times during what we would now call a single day. This faster rhythm matters because tides are not just changes in water level, they create currents. When a large volume of water must move into or out of a basin over a shorter period, the flow can become energetic. Modern tidal channels already demonstrate this on a modest scale. In narrow straits, tidal currents can move rapidly enough to create whirlpools, standing waves, and turbulent water. Scale the system towards stronger forcing and shorter cycles, and early coastal environments could become highly dynamic places. Water would repeatedly cross shallow ground, retreat, and return before the surrounding landscape had experienced anything like a modern 24-hour cycle. Such conditions would have been particularly effective at mixing the oceans. Modern oceans can become layered because water of different temperatures and salinities has different densities. Warm water often remains nearer the surface while colder water stays deeper. Fresh water entering from rain or rivers can sit above saltier water. Winds, currents, convection, and tides all work to mix these layers to varying degrees. Stronger tides on early Earth could provide additional mechanical energy for mixing shallow seas and, under some conditions, deeper portions of ocean basins. Mixing matters for chemistry because oceans are not simply tanks of water. Dissolved minerals, gases, salts, and other compounds are constantly being moved between the surface, the deep ocean, the seafloor, and the atmosphere. Strong tidal currents could increase contact between seawater and newly formed crust. Water moving across volcanic rocks would participate in chemical reactions, dissolving some materials and depositing others. At hydrothermal systems on the seafloor, hot water passing through rock could carry dissolved elements back into the ocean. The exact chemistry of the earliest oceans remains uncertain. but strong physical mixing would have influenced how materials were distributed through them. The coastlines would be chemically active as well. Every tidal cycle could wet exposed rock, leave pools behind, concentrate dissolved substances as water evaporated, and then flood the same surfaces again. Later in Earth's history, environments that repeatedly alternate between wet and dry conditions have attracted attention in research on the origin of life because cycles of concentration and dilution can encourage certain chemical reactions. It would be premature to say that strong early tides caused life to appear, because scientists still debate where and how life's earliest chemistry developed. Hydrothermal vents, freshwater environments, volcanic settings, impact-related systems and tidal zones have all been investigated. The ancient tides simply provided one more source of energy, an environmental cycling on a planet already full of chemical activity. It is also worth remembering that the earliest oceans did not necessarily appear while Earth was still rotating at exactly 5 hours per day. The period immediately following the moon-forming impact was extremely hot. Large amounts of water could have existed as vapour before the surface cooled enough for stable liquid oceans. During that cooling, Earth's rotation was already beginning to slow, so the image of a perfectly developed blue ocean beneath an exact 5-hour clock should be treated as an illustration rather than a snapshot. Earth's day length changed continuously, while the oceans themselves emerged and evolved. There was no single morning when someone could have measured a 5-hour day, looked over a finished ocean, and announced that the conditions were now officially suitable for unusually vigorous tides. As the surface cooled, water vapour condensed and rainfall could begin transferring water from the atmosphere to the ground. Early rain may have fallen onto hot crust and evaporated again before stable bodies of water accumulated. Eventually, temperatures allowed liquid water to remain for long periods, and ancient mineral evidence suggests that this happened surprisingly early in Earth's history. Once broad oceans were present, the Moon's gravitational influence had a very effective medium through which to dissipate Earth's rotational energy. Water is particularly useful in this process because it can move independently of solid rock. The Moon raises a tidal deformation, but Earth rotates beneath it. Because the response is delayed by friction, and because ocean basins interfere with the movement of water, the tidal bulges do not line up perfectly with the Moon. That misalignment allows gravity to create a torque. The Moon pulls backward on the part of Earth's tidal deformation that has been carried ahead, removing a tiny amount of rotational angular momentum. The displaced water and deformed planet pull gravitationally on the Moon in return, adding angular momentum to the Moon's orbit. The energy being lost from Earth's rotation does not disappear. Some becomes heat through tidal friction. Water moving against the seafloor generates turbulence. Internal waves form where currents encounter underwater slopes and ridges. Water masses rub against one another and against boundaries. In the solid Earth, repeated flexing also dissipates energy internally. On the modern planet, tidal dissipation is measurable but modest, compared with the enormous energy involved in Earth's rotation. On the early Earth, stronger tidal forces and a closer Moon meant this mechanism could operate far more powerfully. This would have made ancient coastal environments physically restless. Imagine standing well above an early shoreline for safety, again ignoring the unpleasant question of whether the atmosphere was breathable. Water approaches across a broad shallow shelf. The tide rises quickly compared with the modern cycle. Channels fill. Islands become smaller or disappear temporarily. The current turns around obstacles and forms turbulent wakes. Not many hours later, the process reverses. Water drains back toward deeper parts of the basin. Exposed ground appears. Pools remain in depressions. Then another cycle begins. The sky would be moving rapidly at the same time. The sun crosses from east to west during a day lasting only several hours. The nearby Moon moves through a much faster orbit than the one it follows today. There is no long separation between astronomical events and oceanic response. The entire surface environment is working on shorter cycles. Light, darkness, tidal height, currents, and atmospheric circulation all change quickly by modern standards. Wind would add another layer of motion. Faster planetary rotation strengthens the influence of the Coriolis effect, altering how air and water move across large distances. On a rapidly rotating world, major circulation patterns tend to break into more numerous and narrower bands than on a slowly rotating one. This can influence the paths of winds and ocean currents, and can reduce the size of some large-scale atmospheric structures. But early Earth's atmosphere was unlike today's, making detailed reconstruction difficult. Its pressure, greenhouse gas content, cloud cover, and temperature changed throughout the planet's early history. We should therefore picture rapid rotation as an important influence, rather than assume it produced recognizable modern weather systems moving at 5 times normal speed. Ocean currents would also respond to the faster rotation. The Coriolis effect influences the direction of large-scale currents on modern Earth and helps create enormous rotating gyres in ocean basins. Early oceans under rapid rotation could develop circulation patterns with different characteristic scales. Strong tidal currents would interact with these broader flows. Volcanic islands, shallow shelves, underwater ridges, and young continental fragments would redirect water locally. Where currents met, turbulence could become intense. The seafloor beneath those oceans was itself active. Earth retained much more internal heat than it does today, and volcanic activity played a major role in building and recycling crust. The exact style and timing of early plate tectonics remain debated, but there is little doubt that the planet's interior was energetic. Volcanic eruptions could add new rock to the ocean floor. Hydrothermal circulation moved water through hot crust. Gases from Earth's interior entered the atmosphere and ocean. Impact occasionally disturbed the surface. The ancient ocean was therefore sitting on top of a planet that was still releasing large amounts of heat, while being mechanically stirred by a nearby moon. This could produce enormous local contrasts. One region might contain very hot seawater around a volcanic system, while another had cooler surface conditions. Fresh water from heavy rainfall could temporarily lower salinity near land, while evaporation increased salinity elsewhere. Dissolved iron and other minerals could enter through hydrothermal vents. Without large amounts of free oxygen, many elements behaved chemically differently from the way they do in modern seawater. The familiar blue oxygenated ocean containing fish, plankton, coral and dissolved oxygen did not exist. Even the colour of the ocean is difficult to state confidently. Pure water tends to absorb red wavelengths more strongly and can appear blue in large quantities, but suspended minerals, dissolved iron, volcanic material, and atmospheric conditions could alter how ancient seas looked. Under some chemical conditions, water could appear greenish or darker than modern tropical oceans. Near volcanic regions, it might be clouded by ash and sediments. The young sun was fainter overall than today's sun, and the atmosphere could scatter and absorb light differently. Trying to assign one neat colour to all early oceans is therefore another case where the simple picture is less reliable than the complicated one. The coastlines themselves may not have remained in place for long. Modern humans are used to coastlines changing by metres, or occasionally kilometres during storms, erosion, or long-term sea level rise. Early Earth operated on a different geological background. Volcanic construction could build land, subsidence could lower it. Impacts could remove or reshape regions, crust could fracture and deform. Tides then worked on whatever geography happened to exist at that moment. A strong tidal current repeatedly passing through a narrow channel can erode material and transport sediment. Where the flow slows, that sediment can settle somewhere else. Given enough cycles, tidal processes help reshape their own boundaries. This creates an important feedback. The moon determines the basic tidal forcing, but coastlines and ocean basins determine how effectively that forcing dissipates energy. As tides erode and redistribute material, and as geological processes move continents and change ocean depths, the efficiency of tidal friction changes. That changing efficiency then affects how quickly Earth's rotation slows and how quickly the Moon moves outward. The physical geography of Earth therefore becomes part of the rotational history of the entire Earth-Moon system. This is one reason scientists cannot simply take the modern rate at which Earth's day lengthens and extend it backward at a constant speed. The modern oceans happen to have particular shapes. The Atlantic, Pacific, Indian, Arctic, and Southern Oceans interact with tides in particular ways. Continental shelves and shallow seas dissipate large amounts of tidal energy. Rearrange the continents and the efficiency changes. Remove the present oceans entirely and replace them with a young planet containing different basin depths, and the change can be substantial. Researchers sometimes use ancient sedimentary structures to recover pieces of this lost tidal history. Certain environments deposit repeated layers as tidal currents change strength over daily, monthly, and seasonal cycles. If those layers survive and can be dated reliably, their patterns may preserve information about how many tidal cycles occurred during a month or year. These tidal rhythmites have helped scientists estimate ancient rotation rates and lunar distances for particular periods. They do not reach all the way back to the immediate aftermath of moon formation, but they show that Earth's changing day length can leave physical records in ordinary sediment. Other records come from organisms that built growth bands according to daily and seasonal cycles. Some fossil corals and shells record repeated layers that can reveal the number of days in an ancient year. These records belong to much later periods, when complex life already existed, but they confirm the broad trend predicted by tidal physics. Ancient years contained more days because each day was shorter. The planet was rotating faster and has gradually slowed. The oceans were a major participant in making that happen. Without tidal dissipation, Earth could have retained much more of its early rotational speed. The close moon supplied the gravitational forcing, while Earth's deformable surface and eventually its oceans provided the friction necessary to transfer energy and angular momentum. Every ancient tide was therefore doing two things at once. Locally, it was moving water along shorelines and through ocean basins. Globally, it was contributing an almost unimaginably small amount to the long-term slowing of the entire planet. There is something slightly amusing about the scale difference. A wave runs up an ancient beach and drains away. Nothing dramatic seems to have happened to the planet. Repeat that process across coastlines around the world, combine it with tides in the solid Earth, keep the moon pulling for millions of years, and the rotation changes measurably. Continue for billions of years, and a day that once lasted only several hours becomes a day lasting 24. The tidal energy itself was not constant during that journey. As the moon moved farther away, its tide-producing influence weakened sharply. At the same time, Earth's slowing rotation changed the frequency at which the surface moved through the tidal pattern. Oceans appeared, basins changed, continents formed and moved, and the geography that controlled tidal dissipation was repeatedly reorganized. The system was always adjusting. During the earliest period, when the moon was extremely close, tides in the solid Earth may have played a particularly important role. A still-hot planet with molten or partially molten layers could deform significantly under the moon's gravitational pull. As liquid oceans developed, they added another mechanism for dissipation. Later, as Earth's interior cooled and the arrangement of oceans changed, the balance between different sources of tidal friction changed as well. There was no single type of tide operating with identical strength from the birth of the moon until today. Strong tides may also have influenced the exchange of gases between ocean and atmosphere. Turbulent water exposes more surface area and can mix dissolved gases through the upper ocean. Waves and breaking currents stir the surface. Chemical compounds arriving from volcanic eruptions or rainfall can be redistributed. In shallow coastal environments, repeated flooding allows water to interact with fresh minerals and then carry dissolved products back to the sea. None of this requires enormous fictional tidal waves. Ordinary physics applied with stronger forcing and repeated over immense stretches of time is enough to produce an active environment. If life had already emerged while tides remained especially strong, these cycles would have become part of the environment organisms had to tolerate. The precise timing of life's origin remains uncertain, so we cannot confidently place living communities on the most extreme 5-hour-day coastline. By the time we have stronger evidence for early life, Earth's rotation had already slowed from its immediate post-impact state. Even then, however, days were shorter than they are now, and the Moon was substantially closer. The earliest organisms therefore evolved on a planet with a different tidal and rotational rhythm from modern Earth. For microorganisms, tides can transport nutrients and carry cells between environments. Shallow water heats and cools more quickly than deep water. Sunlight reaches the bottom in some regions while deeper zones remain dark. Wet-dry cycles change concentrations of salts and organic compounds. Strong mixing can supply chemical ingredients while also making conditions less stable. Whether that helped or hindered particular steps toward life depended on the environment, and scientists continue to investigate multiple possibilities rather than settling on a single ancient shoreline as the birthplace of biology. What is much clearer is that tides were constantly extracting rotational energy from Earth. This is the connection that runs through the entire story. The Moon's closeness produced strong tides. Strong tides created friction and deformation. That friction slowed Earth's spin. The slowing transferred angular momentum into the Moon's orbit. The Moon moved farther away. A more distant Moon produced weaker tidal forcing. The system gradually became less extreme. The oceans were therefore not simply being affected by the changing Earth-Moon relationship. They were helping drive it. Their movement was one of the mechanisms through which a rapidly spinning planet could lose rotational energy. The length of every future day was being altered, by tiny amounts, through the repeated movement of water. If we could accelerate the scene and watch millions of years pass in minutes, the trend would become visible. The young Moon slowly shrinks in apparent size as its orbit expands. The furious tidal forcing begins to weaken. Earth's rotation becomes less frantic. Sunrises arrive farther apart. Ocean basins appear, disappear, and change shape. Continents reorganize. The day keeps lengthening, though not at one perfectly constant rate. Nothing ever reaches a moment when the tides announce that their work is finished. They are still doing it now. The oceans outside modern coastlines continue to rise and fall. The solid Earth continues to flex. The Moon continues to receive angular momentum and move outward. The only reason the effect feels absent from ordinary life is that the change from one day to the next is extremely small. To turn a 5-hour day into the much longer days that followed, however, small changes were enough because time supplied billions of years in which to accumulate them. The young oceans may have looked chaotic from the shoreline, but the most important result of their tides was happening much more quietly. Each cycle placed a tiny break on Earth's rotation, and that break would eventually transform the basic pace of the planet. The tidal movement of the ancient oceans was doing something far more important than rearranging water along the coastline. Every time the Moon raised a tidal deformation on Earth, a tiny amount of the planet's rotational energy was being lost. The effect of any single tide was almost nothing compared with the enormous amount of energy stored in a spinning planet. But the Moon did not pull on Earth once and then stop. It kept pulling through every rotation, every orbit, every changing ocean basin, and every rearrangement of the continents. Given enough time, that repeated gravitational interaction acted like a brake. It was not a brake in the ordinary sense, because nothing was rubbing against Earth from the outside. Instead, gravity, tides, friction, and the conservation of angular momentum slowly transformed the way the Earth-Moon system moved. The easiest place to begin is with the tidal bulges themselves. If Earth were covered by a perfectly deep ocean and didn't rotate, the simplest picture would place one broad tidal bulge on the side facing the Moon and another on the opposite side. The real Earth is much messier because continents interrupt the oceans, coastlines redirect water, seafloor depth changes constantly, and the planet is rotating beneath the tidal pattern. Even so, the basic idea survives. The moon's gravity stretches Earth slightly along the line between the two worlds. The oceans respond strongly because water can move, while the solid Earth responds by flexing by smaller amounts. Now add rotation. Earth turns much faster than the moon goes around it. That is true today, and it was even more dramatically true when Earth's day lasted only a few hours. As the planet rotated, it carried the tidal response slightly ahead of the position directly beneath the moon. Friction inside the oceans and solid Earth prevents the tidal bulge from instantly following the moon's position. The result is that the bulge becomes offset. That small offset is the heart of the braking process. The moon pulls gravitationally on the bulge that has been carried ahead. Because that pull acts slightly backward against Earth's direction of rotation, it applies a torque that slows the planet. The effect is tiny from one moment to the next, but it removes rotational angular momentum from Earth. At the same time, the tidal bulge pulls forward on the moon. That forward gravitational tug adds angular momentum to the moon's orbit. Earth slows down, the moon moves outward. Those two changes are linked. It is tempting to think that the moon moves farther away because Earth's gravity is somehow weakening, but that is not what is happening. Earth's gravity remains more than strong enough to keep the moon in orbit. The moon is moving outward because it is receiving angular momentum from Earth's rotation. As its orbit gains angular momentum, the size of the orbit increases. The moon becomes more distant and its orbital period becomes longer. Meanwhile, Earth's rotation becomes slower, so the length of the day increases. The strange part is that the system is essentially using one kind of motion to modify another. Earth's spin is losing angular momentum while the moon's orbit gains it. The total angular momentum of the Earth-Moon system remains approximately conserved when outside influences are ignored, but its distribution changes. More of it moves into the moon's orbital motion and less remains in Earth's rapid spin. A simple comparison is a person sitting on a rotating chair while holding a heavy object. If the mass is moved farther from the axis of rotation, the rotational behaviour changes. The Earth-Moon system is not literally connected by rigid arms, of course, so the mechanism is different, but the same conservation principle is operating. Moving mass and angular momentum farther from the central axis changes how quickly the central body rotates. Another familiar comparison comes from figure skating. A spinning skater rotates rapidly with arms pulled close to the body and slows when those arms extend outward. Again, Earth and Moon are not one solid object, but the broad lesson is useful. A system with more of its angular momentum distributed farther away tends to rotate differently from one in which that angular momentum is concentrated near the centre. The early Earth-Moon system began in a much more compact state. The Moon was close, and Earth was spinning quickly. Over time, angular momentum shifted outward. The Moon's orbit expanded, and Earth's rotation slowed. This process was strongest when the Moon was closest. That follows from the way tidal forces depend on distance. The Moon's tide-producing influence weakens rapidly, as the distance between Earth and Moon increases. A nearby moon therefore deformed Earth far more strongly than the modern Moon does. Stronger deformation generally creates more opportunity for energy to be dissipated through friction. On the young Earth, the solid planet itself could absorb tidal energy because its interior was hotter and in some stages more deformable than it is today. Later, once extensive oceans existed, water became an especially effective way of dissipating tidal energy. Tidal currents moved across sea floors and through narrow passages. Internal waves formed when currents crossed underwater ridges. Turbulence broke organised motion into smaller and smaller movements until energy eventually appeared as heat. That heat was not enough to keep Earth molten or dramatically warm the entire planet, but from the perspective of rotational mechanics, it represented something important. Energy that had once been part of Earth's orderly spin had been converted into disorganized thermal motion. This is why tidal friction is called friction, even though the Moon never physically touches Earth. The gravitational interaction creates motion, and that motion loses mechanical energy through deformation and turbulence. The solid Earth contributes as well. Our planet is not perfectly rigid. Even today, the crust and mantle rise and fall slightly under the gravitational influence of the Moon and Sun. Repeated deformation inside solid material also dissipates energy. On a hotter, younger Earth, the way the mantle responded to these forces would have been different, and the balance between solid Earth tides and ocean tides probably changed over time. The breaking rate was therefore never perfectly constant. That point matters because it is easy to imagine Earth's day lengthening at one simple steady pace from 5 hours to 24. Reality was far more complicated. Tidal dissipation depends on where the continents are, how deep the oceans are, how coastlines are shaped, and how well particular ocean basins resonate with tidal forcing. A basin with a natural oscillation period close to the tidal forcing period can respond strongly. Water moves farther and faster, increasing friction and energy loss. Another basin with a different geometry may respond less efficiently. As plate tectonics rearranges continents, the effectiveness of tidal braking changes. Earth has repeatedly reorganized its surface over geological time. Continents have collided into supercontinents and later broken apart. Oceans have opened and closed. Shallow continental shelves have appeared and disappeared as sea level changed. All of those changes influence tides. So the Moon was always applying the basic gravitational forcing, but Earth itself decided in a sense how efficiently that forcing would be converted into rotational braking. The modern arrangement of continents happens to produce substantial tidal dissipation in the oceans. That does not mean the same rate existed hundreds of millions or billions of years ago. Some ancient continental arrangements may have produced weaker tidal friction, allowing Earth's rotational slowdown to proceed more slowly for a period. Other arrangements may have increased dissipation. This irregular braking is one reason reconstructing the exact history of Earth's day length is difficult. Scientists cannot simply take the present rate of change and run it backward like a perfectly reliable clock. Instead, they look for physical records left behind. Some ancient sediments contain repeated tidal layers. Water moving in and out of shallow environments can deposit sand, silt, and mud in patterns connected to tidal cycles. If enough of those layers survive, researchers can sometimes identify daily, monthly, and seasonal groupings. These rocks act like damaged but readable calendars. Suppose a sedimentary sequence shows repeated small layers grouped into larger cycles associated with lunar variations. The number of daily layers inside a longer cycle can provide information about how many Earth rotations occur during a lunar month at that time. Combine that with estimates of the length of the year, and researchers can begin reconstructing ancient day length. Later in Earth's history, living organisms provided other records. Some corals, mollusks, and other organisms grow in repeated bands influenced by daily and seasonal cycles. Fossil growth patterns can therefore preserve evidence that ancient years contained more days than modern years. The important reason is not that the year itself was dramatically longer. It is that the days were shorter. Imagine a year lasting roughly the same amount of orbital time, but made from 20-hour days instead of 24-hour days. More rotations fit into one trip around the Sun. The calendar would contain more days, even though the planet's orbital motion had not changed nearly as dramatically. Go farther into the past and the difference becomes larger. When Earth was spinning extremely rapidly, a year could contain far more rotations than the 365 we experience now. A 5-hour day would allow well over 1,000 rotations during something close to a modern length year. There were no calendars then, but the mechanics are straightforward. The Sun would rise again and again while Earth slowly made its annual journey around its star. Someone using modern language might say the year contained an absurd number of days, but the universe would not consider the number absurd. It would simply reflect the speed at which one motion happened compared with another. The Moon's braking changed that ratio. As Earth slowed, fewer rotations fit into each year. The number of days gradually fell. A planet that once experienced more than 1,000 rotations during one orbit eventually experienced hundreds instead. This did not happen evenly. There may have been long periods when day length changed relatively slowly, and other intervals when tidal dissipation was more efficient. But the overall direction was toward longer days. There is a useful way to appreciate how difficult the change would be to notice in real time. Imagine living during some period of ancient Earth when the day happened to last 18 hours. Your entire life passes under that 18-hour rhythm. Your parents experienced nearly the same day length. Your grandparents did as well. So would thousands of generations before you. Nothing about daily experience would suggest that the planet was undergoing a major transformation. Yet compare your era with another separated by hundreds of millions of years, and the difference becomes obvious. This is one of the recurring tricks of deep time. Geological processes can be enormous without being fast. Mountain ranges rise while no individual observer sees them moving. Continents cross oceans at speeds comparable to the growth of fingernails. Species change across generations too slowly for any one animal to notice evolution happening around it. Earth's rotational braking belongs to the same category. The Moon never had to slow the planet dramatically in a single year. It simply had to keep applying a tiny torque for an extremely long time. That torque is still operating. Modern measurements show that Earth's rotation is not perfectly constant. The long-term tidal effect tends to increase the length of the day, but shorter-term processes can temporarily speed Earth up or slow it down by small amounts. Winds move mass through the atmosphere. Ocean currents redistribute water. Seasonal snow and ice shift mass across the surface. Earthquakes can rearrange tiny amounts of the planet's mass. Movements in the liquid outer core interact with the mantle. Even climate-driven changes in ice and groundwater can affect the distribution of mass enough to produce measurable changes in rotation. This means the length of one particular modern day can vary slightly. But beneath those short-term fluctuations sits the much longer tidal trend. The Moon is still extracting rotational angular momentum. The day is still, over sufficiently long periods, becoming longer. And the Moon is still moving farther away. The modern recession is only a few centimeters per year. That is roughly the speed at which fingernails grow, depending on the fingernails and the amount of attention someone is willing to give them. It hardly sounds like the mechanism responsible for transforming a 5-hour Earth into a 24-hour Earth. The trick, once again, is time. 4 centimeters multiplied over 1 year is nothing astronomical. 4 centimeters repeated over millions of years becomes tens of kilometers. Repeat the interaction across billions of years, while allowing the recession rate itself to change, and the architecture of the Earth-Moon system becomes completely different. The Moon's orbit today is hundreds of thousands of kilometers from Earth. Near its formation, it was dramatically closer. The change in apparent size would have been obvious if anyone had existed to watch long enough, although watching long enough would have required several 100 million years and an unusually patient observer. The changing orbit also affects the length of the lunar month. A closer satellite orbits more quickly. As the Moon moved outward, it took longer to complete each orbit. The ancient lunar month therefore contained different numbers of Earth days depending on the era. This relationship between the lengthening day and lengthening month creates an interesting moving target. Both clocks are changing at once. Earth slows, increasing the duration of a day. The Moon moves outward, increasing the duration of its orbit. The ratio between them changes through time. At certain points in the distant past, the number of Earth days in one lunar month was very different from today's value. Later, life evolved under those changing cycles. Early microorganisms did not experience the same daily and lunar rhythm as modern coastal organisms. Plants, once they appeared on land, inherited a different day length from the one we experience now. Paleozoic animals lived under shorter days. Dinosaurs lived under days somewhat shorter than 24 hours. No species received a notification that the planetary clock had been adjusted. Their biological systems simply evolved under the conditions available. This raises an interesting connection between astronomy and biology. Organisms on modern Earth have internal circadian systems closely connected to the approximately 24-hour day-night cycle. But the day has not always been 24 hours. That does not mean ancient life was confused. Circadian rhythms evolve, organisms respond to environmental cycles, and over geological time, natural selection can tune biological clocks to changing conditions. The important point is that biology had to follow astronomy, not the other way around. Earth's rotation determined the light-dark cycle. The moon helped change the rotation. Life adapted. There may even have been periods when the lengthening of the day slowed substantially, because Earth's atmosphere interacted with solar heating in a way that partially opposed lunar tidal breaking. Atmospheric tides are real. Sunlight warms the atmosphere differently across the day, producing large-scale pressure oscillations. Those atmospheric tides can transfer angular momentum to Earth. Under certain conditions, the natural period of atmospheric oscillation can approach the forcing period from solar heating, creating resonance. Some researchers have proposed that this effect may once have balanced part of the moon's braking torque and temporarily kept Earth's day near a particular length for an extended geological period. The details remain an area of research, but the possibility illustrates how many parts of Earth participate in rotation. The moon is the dominant long-term brake, but the oceans, atmosphere, mantle, core, climate and continental arrangement all influence the exact path. A day is therefore not simply set by how hard the moon pulls. It emerges from an entire planetary system exchanging energy and angular momentum. Even changes in the moon itself mattered. The moon cooled internally after formation. It became tidally locked. Its orbit evolved in shape and orientation. Gravitational interactions with the Sun affected its path. Earth and Moon together orbit the Sun, so the system has never been completely isolated. Yet the broad result remains remarkably simple. The early Earth spun quickly. The nearby Moon raised strong tides. Friction caused the tides to lag or lead in a way that produced torque. Earth lost rotational angular momentum. The Moon gained orbital angular momentum. Earth's day lengthened. The Moon moved outward. That process explains why the sky no longer races past us in 5 hours. It also tells us something surprising about the Moon itself. The Moon is not merely a witness to Earth's history. It helped create the pace at which that history unfolded. Every geological event on the surface happened under a rotation rate, partly shaped by lunar gravity. Every ancient sunrise occurred according to a day length produced by the ongoing exchange between Earth and Moon. Every organism that evolved under a particular cycle of daylight and darkness inherited an environment that the Moon had helped regulate. Even modern human schedules ultimately sit on top of this astronomical history. We call 24 hours a normal day, because that is the rotation period Earth happens to have during the tiny slice of geological time in which humans exist. Nothing about 24 is sacred. Had the Earth-Moon system evolved differently, civilization might have developed under 20-hour days, 30-hour days, or some other rhythm entirely. Our clocks would divide whatever cycle existed. People would still complain about mornings. The numbers on the clock would simply be different. The future will also be different, although the change is extremely slow. As long as the Moon continues moving outward and tidal friction continues transferring angular momentum, Earth's rotation will keep slowing over long periods. Days millions of years from now will be slightly longer than hours. Farther into the future, the difference becomes larger. In an idealized system allowed to evolve long enough without the Sun changing or other major disruptions, Earth and Moon would tend toward a state in which Earth rotated at the same rate that the Moon orbited. Both bodies would keep the same face toward one another, much as the Moon already keeps nearly the same face toward Earth today. This condition is called mutual tidal locking. Pluto and its large moon Charon provide an example. Charon is tidally locked to Pluto, and Pluto is also locked to Charon. From one side of Pluto, Charon would appear to remain almost fixed in the sky, because Pluto's rotation period matches Charon's orbital period. Earth and Moon are nowhere near that state today. The Moon is already locked to Earth, but Earth still spins far more quickly than the Moon orbits. The tidal interaction therefore continues transferring angular momentum outward. Long before the Earth-Moon system could naturally reach complete mutual locking, however, the Sun's evolution would drastically alter conditions in the solar system. So the theoretical final state is more useful for understanding the direction of tidal evolution than as a realistic prediction of what humans or even Earth will eventually experience. For the ancient world, the important part is what happened during the first billions of years. Earth began with a very short day. The Moon began close. The strongest tidal breaking occurred early. The rotation slowed rapidly compared with the much weaker rate operating today. As the Moon receded, the breaking weakened. Days became longer more gradually. By the time complex animals became common, Earth's day was already much closer to the modern value, though still measurably shorter. This means the transition from 5 hours to 24 was not a smooth straight line on a graph. The early part of the story changed quickly, later sections stretched out. The farther the Moon moved away, the less powerfully it could raise tides, and the less efficiently it could continue breaking Earth, all else being equal. Other geological changes then modified that background trend. The result is a complicated history written across astronomy and geology. If we could place markers at different points in Earth's past and measure the length of the day at each one, we would watch the planetary rhythm gradually relax. Near the beginning, the Sun races overhead. Later it crosses the sky more slowly. At another marker, the day lasts perhaps 10 or 15 hours. Farther forward, 20. Later still, 22. Eventually we reach the world we recognize, where the rotation period is close enough to 24 hours that an entire civilization has built its definition of a day around it. At every step, the Moon is farther away than it was before. That is the connection to keep in mind. A longer day and a more distant Moon are two sides of the same history. When the Moon moves outward, it is carrying with it angular momentum that once helped Earth spin faster. The distance in the night sky is therefore partly a record of Earth's lost rotation. The Moon has been taking the energy of the young planet's frantic spin and gradually storing the motion in a wider orbit. Not stealing it exactly. The laws of physics are less dramatic than that. But redistributing it. Patiently, tide after tide. The oceans helped. The mantle helped. The changing shape of the planet helped. Continents altered the efficiency. Atmospheric motion occasionally complicated things. Yet through all of those details, lunar gravity kept the overall process moving in the same direction. A world that once completed an entire day before a modern morning was finished began settling into a slower rhythm. And as that rhythm changed, the number of days in a year changed with it, leaving behind clues in rocks, sediments, fossils, and astronomical calculations that allow us to follow the lengthening day across geological time. That trail is what lets us move away from the almost unimaginable 5-hour Earth and begin stepping through the intermediate worlds that followed, when the day lasted 10 hours, 15 hours, 20 hours, and eventually approached the 24-hour cycle that now feels so permanent. Once the Moon had begun carrying angular momentum away from Earth's rotation, the 5-hour day was already on borrowed time. Not borrowed in the usual human sense, where something is expected back by Thursday and eventually disappears forever into a cupboard, but borrowed on a geological scale. Earth was not going to keep spinning that quickly. The nearby Moon was raising strong tides. Those tides were dissipating energy, and the planet's rotation was gradually slowing. What makes the story difficult to picture is that the change took place across such an enormous span of time that no single moment looks particularly dramatic. There was no point when Earth suddenly paused, reconsidered its schedule, and added another hour to the afternoon. The day lengthened by tiny amounts, while the Moon moved outward by tiny amounts, and the two changes accumulated over billions of years until the world arrived at the 24-hour rhythm we treat as normal today. If we could somehow watch the entire process from a safe position in space and speed it up enormously, the change would be obvious. Near the beginning, Earth rotates almost impatiently. The planet turns again and again while the Moon moves around it in a much tighter orbit. The Sun appears to rise frequently for any point on the surface. As millions of years pass in seconds, the rotation begins to relax. The Moon drifts outward. 5-hour days become longer days. The apparent movement of the sky slows. The number of rotations Earth completes during one trip around the Sun begins to fall. Nothing else on the planet stays still during this process either. The crust cools, oceans develop, impacts become less common, continents begin forming and changing, the atmosphere evolves, and eventually life appears. The lengthening day quietly continues through all of it. The exact path from 5 hours to 24 is not known minute by minute, or even hour by hour across every interval of geological time. We can calculate the basic physics of tidal evolution, but Earth is too complicated for one simple equation to provide a perfect history. The rate at which the planet loses rotational energy depends partly on how efficiently tides dissipate that energy. Oceans are particularly important, and oceans keep changing. Their depths change, continents move, shallow seas appear and disappear. Mountain building alters coastlines, supercontinents form and break apart. All of this changes the way tidal waves move through ocean basins, which means the Moon's braking effect has sometimes been more efficient and sometimes less efficient. The earliest part of the slowdown was probably very different from what we observe today. The Moon was much closer, so the tide-producing force was stronger. Earth was also hotter, and its interior and outer layers responded differently to deformation. The planet may have lost rotational energy comparatively quickly during this period. As the Moon moved farther away, its tidal influence weakened. The process did not stop, but the strength of the interaction changed. This is why it would be misleading to take the modern rate at which Earth's day lengthens and simply run that rate backward for 4.5 billion years. Doing so would pretend that the Moon has always been at roughly the same distance, that Earth's oceans have always had the same shapes, and that nothing interesting has happened to the planet since its formation, which would be a remarkably unfair description of Earth's behaviour. Scientists therefore have to reconstruct the history using several different kinds of evidence. Physics tells us how tidal interactions should move angular momentum between Earth and Moon. Astronomy gives us the present masses, orbit, and rotation of the system. Geology then provides snapshots from particular moments in the past. Some of the most useful snapshots come from rocks that preserve repeated tidal patterns. In certain shallow water environments, tides move sediment in ways that can create regularly repeating layers. Stronger currents may deposit coarser material, weaker currents, finer material, and longer cycles connected with changes in the Moon's position can group those layers into recognizable patterns. These structures are sometimes called tidal rhythmites, and they are about as close as geology gets to finding an old calendar written in mud. The individual layers can correspond to repeated tidal cycles, while larger groupings may reflect longer lunar or seasonal patterns. By counting those repetitions and working out how quickly the sediments accumulated, researchers can estimate how many tidal cycles occur during longer astronomical periods. From there, they can infer information about the length of the ancient day in the Moon's orbit. This requires considerable care because rocks are not known for maintaining perfect paperwork over hundreds of millions of years. Layers can be disturbed, compressed, eroded, or altered chemically. A pattern that appears regular may have more than one possible explanation. Researchers therefore compare sedimentary evidence with astronomical models rather than trusting one rock exposure to settle the entire history of planetary rotation. Even with those difficulties, ancient tidal deposits have provided valuable evidence that the Moon was closer in the past and Earth's days were shorter. Later in Earth's history, living organisms began keeping another kind of accidental time record. Some organisms build shells or skeletons in layers that respond to daily and seasonal cycles. Growth can change with light, temperature, food availability, or other environmental factors. In certain fossils, researchers can examine repeated bands and estimate how many daily growth increments occurred within a year. Fossil corals are a famous example. Corals living hundreds of millions of years ago could preserve fine growth lines associated with daily cycles and broader bands associated with annual growth. When researchers count the daily increments contained within a year, they sometimes find more than 365. That does not mean ancient Earth needed extra months to accommodate an unusually enthusiastic calendar. It means the year contained more days because the days themselves were shorter. During parts of the Paleozoic era, for example, Earth may have experienced days of roughly 21 or 22 hours rather than 24. A year could therefore contain around 400 daily rotations instead of 365. The exact values vary depending on the period and evidence being examined, but the overall pattern is consistent with tidal slowing. Move backward through geological time and the days become shorter. Move forward and they become longer. This can feel counterintuitive because we are used to treating the year and the day as parts of the same calendar system. One year contains a certain number of days, so it is easy to imagine that changing one somehow has to change the other in the same proportion. Astronomically, they come from different motions. The day is mainly determined by Earth's rotation. The year is determined by Earth's orbit around the Sun. Slow the rotation while leaving the orbit broadly similar, and the year still lasts about the same amount of absolute time, but fewer rotations fit inside it. Think of someone walking around a circular track while also spinning in place. The time needed to complete the lap and the time needed for each spin are separate things. If the person begins spinning more slowly but continues walking around the track at about the same rate, fewer spins occur during each lap. Earth works in the same general way, although fortunately our planet does not become dizzy. On the earliest fast-spinning Earth, more than 1,000 rotations could fit into something close to a modern-length year if the day were around 5 hours. As the day stretched toward 10 hours, the number of rotations per orbit dropped dramatically. At 15 hours, it dropped again. By 20 hours, the year contained hundreds fewer days than it had near the beginning. Eventually, as the rotation approached its modern speed, the familiar number of roughly 365 solar days emerged. There was never anything special about 365 either. It is simply the ratio that happens to exist now between Earth's rotation and its orbit. Had the Moon been smaller, farther away, or absent entirely, Earth's rotational history might have been different. The modern year could contain a different number of days. Human civilizations would then have developed calendars around that number and regarded it as perfectly ordinary. This is one of those places where the familiar world begins to look less inevitable. 24 hours seems built into daily life because everything we do assumes it. Sleep schedules, working hours, meal times, television programming, train timetables, school days, and the deeply optimistic phrase, "I'll do it tomorrow," all depend on the length of the day. But 24 hours was not chosen for us. It emerged from billions of years of planetary history. The young Earth passed through many day lengths before arriving here. There must have been periods when the day lasted 6 hours, 8 hours, 10 hours, and every intermediate value between them. These were not separate eras with clean boundaries. A day of 8 hours and 12 minutes eventually became 8 hours and 13 minutes, though the difference took a very long time to accumulate. The process was continuous. At some point, Earth passed a 10-hour day. Later, it crossed 12. Much later, it moved beyond 18 and 20. No geological clock announced these milestones. From the perspective of anything living during one of those periods, the day length simply seemed fixed. Suppose an organism lived when Earth's day lasted 21 hours. Its entire biological world would be built around that cycle. Light and darkness would repeat every 21 hours. Temperatures would respond accordingly. Tides would follow the combination of Earth's rotation and the Moon's shorter orbit at that time. Organisms with internal biological clocks would evolve within that environment. 21 hours would not feel short. It would simply feel like a day. Only by comparing widely separated periods could anyone notice the trend. This is why deep time can be difficult for the human mind. We are good at noticing fast changes. A storm arriving over an hour feels obvious. A season changing over several months is easy to understand. Even the growth of a child over several years can surprise us when we compare photographs. But a change that needs tens of millions of years to become noticeable does not fit naturally into everyday experience. The lengthening of the day operates on that scale. Modern Earth's rotation changes by tiny amounts, and the long-term tidal contribution is usually discussed in milliseconds over centuries rather than minutes over years. Human history is too short to experience the enormous change directly. Even written civilization represents only a tiny fraction of the period over which tidal breaking has operated. Yet the moon has been there through almost the entire story. Before animals existed, it was slowing Earth. Before photosynthesis transformed the atmosphere, it was slowing Earth. Before continents had anything resembling their present arrangement, it was slowing Earth. When the first complex cells appeared, the day was already longer than it had been near Earth's formation, and the moon was already farther away. When multicellular animals diversified in the oceans, the day had lengthened further. When plants spread across land, the rotation continued slowing. When forests became widespread and early reptiles appeared, the moon kept moving outward. When dinosaurs walked across the continents, their days were slightly shorter than ours. When the first members of our own lineage appeared much later, the day was already extremely close to 24 hours. The difference between a dinosaur's day and ours would not have been dramatic enough to make a visitor immediately confused. We're talking about modest differences by then, not a return to the 5-hour world. But the difference is another reminder that the clock kept changing even during eras we often imagine in otherwise familiar 24-hour terms. There is an interesting practical question here. If the day was shorter, did everything happen faster? Did dinosaurs have to sleep more quickly? Did ancient plants rush through photosynthesis before sunset? Not exactly. Biological processes adapt to environmental rhythms. Organisms did not experience shorter days as accelerated versions of our own. Their physiology evolved under the conditions that existed. Modern circadian rhythms provide a good example. Many organisms have internal cycles close to the length of the environmental day, but these rhythms are not perfect mechanical clocks. They can adjust to light, temperature, food availability, and other cues. Over evolutionary time, populations can adapt to different cycle lengths. Ancient life, therefore, had plenty of time to evolve alongside Earth's gradually changing rotation. The change in day length may also have influenced the environment itself. A slower rotation changes the way the atmosphere and oceans respond to heating. The Coriolis effect becomes somewhat weaker as rotation slows, which can alter the characteristic size of circulation systems. The duration of daylight and darkness increases, giving surfaces more time to warm and cool during each cycle. Tidal frequencies change. None of this means that Earth's climate was controlled mainly by day length, because greenhouse gases, solar brightness, continental arrangement, ocean circulation, and many other factors were enormously important. But rotation was one part of the background conditions under which the climate system evolved. The young sun was also gradually becoming brighter during this time. The continents were growing and reorganizing. The atmosphere changed from one with almost no free oxygen to one in which oxygen eventually became abundant. Life changed the chemistry of the oceans. Plate tectonics continued reshaping the surface. The lengthening day was therefore taking place inside a planet where almost every other major system was changing too. For researchers trying to reconstruct ancient rotation, this creates both opportunities and problems. Geological layers influenced by tides may preserve useful timing information, but the continents that produced those tides were not in their modern positions. Fossils may preserve daily growth bands, but biological growth can also respond to environmental stress. Numerical models can calculate tidal evolution, but they need assumptions about ancient ocean depth and geography. This is why estimates of ancient day length are usually given with uncertainty rather than as exact clock readings. Saying that Earth had a day of roughly a certain length during a particular era is very different from claiming that every day lasted exactly 21 hours, 14 minutes, and 37 seconds. Deep time science rarely provides that kind of precision. Even the modern 24-hour day is slightly misleading if taken too literally. There are several ways to define a day. Earth's rotation relative to distant stars produces the sidereal day, which is a little under 24 hours. The familiar 24-hour solar day measures the average interval between successive noons as Earth rotates, while also moving along its orbit. Because Earth advances around the Sun during each rotation, it has to turn a little farther than one full rotation relative to the stars before the Sun returns to the same position in the sky. For everyday life, we smooth these details into the convenient 24-hour civil day. Clocks divide it into hours, minutes, and seconds, and civilization continues without everyone needing to discuss orbital geometry before breakfast. The fact that we can make such precise measurements today gives us another view of how much the planet has changed. Atomic clocks can detect extremely small variations in rotation. Astronomers can measure the moon's recession using laser ranging. Satellites monitor changes in Earth's mass distribution. We can observe seasonal shifts caused by winds and ocean currents. The day that feels perfectly constant to us is actually varying by tiny amounts all the time. Some of those variations temporarily make Earth rotate slightly faster, others slightly slower. Strong winds can exchange angular momentum with the solid planet. Ocean currents do the same. Changes in ice sheets and groundwater redistribute mass. Motions in Earth's core can alter rotation over longer periods. The long-term lunar tide sits underneath this complicated pattern, steadily pushing towards slower rotation. This makes Earth's rotational history less like a smooth ramp and more like a long downward trend in speed with many small wiggles along the way. Over days or years, the wiggles matter. Over hundreds of millions of years, the tidal trend becomes unmistakable. The 24-hour day we know is therefore not a final destination. It is simply where the planet happens to be now. Earth's rotation will continue changing. The moon is still moving outward. Tidal friction is still operating. Future days will become slightly longer for sufficiently long periods. The change is far too slow to affect a human schedule. You do not need to prepare for a 25-hour day next month. The extra time would be useful, but unfortunately the moon has not arranged anything so convenient. Changes of that size require geological timescales. Far enough into the future, assuming the Earth-Moon system were allowed to continue evolving without the Sun dramatically altering the situation, Earth's rotation could eventually approach synchronization with the Moon's orbit. At that point, Earth would keep roughly the same face toward the Moon, just as the Moon currently keeps nearly the same face toward Earth. The day and lunar month would become linked in a completely different way, but the Sun will evolve long before that simple tidal endpoint becomes relevant. The future Earth will face much larger changes as solar brightness increases and the Sun eventually leaves its current main sequence stage. So the 24-hour day belongs to a temporary window between a rapidly spinning young planet and a distant future shaped by processes far larger than our clocks. For now, though, 24 hours is what we have. It is easy to look at that number and see only a unit of time. There are 24 hours in a day because there are 24 hours in a day. We learn it as children and rarely ask where the number came from. The answer is that the number is partly astronomical history. It comes from the giant impact that helped create the Moon. It comes from the close lunar orbit that followed. It comes from tides deforming the young Earth. It comes from friction in molten rock, solid mantle, shallow seas, and deep oceans. It comes from continents shifting into arrangements that sometimes strengthened tidal dissipation and sometimes weakened it. It comes from billions of years during which angular momentum gradually moved away from Earth's spin and into the Moon's orbit. The hour itself is a human invention. Nature did not divide the rotation into 24 equal pieces and leave instructions. Ancient civilizations eventually created systems for dividing daylight and darkness, and later clocks standardized those divisions more precisely. But the total duration we are dividing comes from the physical rotation of the planet. Had we appeared much earlier, our clocks would have been built around another world. A 12-hour Earth would not necessarily have 12 of our modern hours in a day, because civilizations would probably define units differently. People might divide the rotation into 24 shorter hours and consider those units perfectly ordinary. That is another reason it helps to focus on rotation rather than the labels attached to it. Earth turns. We choose how to count the turning. For almost all of Earth's existence, no one counted at all. The planet simply passed through one rotation after another, while the Moon gradually altered the pace. A 5-hour day became 6, 6 became 7. Eventually the planet passed through day lengths that would still seem very short to us, then through ones that would feel almost familiar. By the age of dinosaurs, the difference had become comparatively small. By the time humans appeared, Earth's rotational rhythm was close to the one that would shape agriculture, sleep, navigation, clocks, time zones, work schedules, and nearly every other part of civilization. And the change has not stopped. Tonight's sunset happened a tiny bit later in Earth's rotational history than sunsets experienced by people thousands of years ago. The difference is far too small to notice without careful measurement. But the Moon has continued doing what it has been doing since the beginning. It keeps pulling. Earth keeps responding. The orbit keeps expanding. The rotation keeps evolving. The 24-hour day feels permanent only because human lives are short. Viewed across the full history of the planet, it is one frame in a very long sequence. That leaves one last part of this story sitting beneath everything we have discussed. Earth is no longer the frantic young planet racing through 5-hour rotations, but it has not stopped changing either. The same system that carried us from those first short days into the familiar rhythm of morning and night is still operating above us now. Measurable, with modern instruments, and continuing to alter the planet one almost impossibly small moment at a time. The 24-hour day feels fixed because for all practical purposes, it is fixed during a human lifetime. You can buy a clock today, hand it to someone decades from now, and neither of you will need to redesign the dial because Earth has suddenly added another hour to Tuesday. Yet the process that carried our planet from those extremely short early rotations to the day we know has never actually stopped. The Moon is still pulling on Earth, the oceans are still responding, the solid planet is still flexing, angular momentum is still being transferred outward, and over sufficiently long periods Earth's rotation is still slowing. The difference is that the effect has become very small compared with the violent early period when the Moon was much closer. What once helped transform a world with days lasting only several hours now changes the length of the day by amounts that require extremely precise instruments to detect. Earth has not reached a permanent rotational setting. It has simply reached a stage where the change is far too slow for us to notice while living ordinary lives. Modern measurements make this especially interesting because our clocks have become much more reliable than the planet they are measuring. For most of human history, that situation was reversed. People defined time largely by watching Earth turn. Noon was connected to the sun reaching its highest point in the sky. Days were based on the cycle of a light and darkness. Later mechanical clocks divided those cycles more precisely, but the rotating Earth remained the basic reference. Atomic clocks changed the relationship. They measure time using extremely stable atomic transitions rather than depending on Earth's rotation, and they are precise enough to reveal that Earth does not complete every rotation in exactly the same amount of time. The astronomical day can be slightly longer or slightly shorter than the neat 86,400 seconds assigned to our civil 24-hour day. The differences are tiny, But once your clock becomes sufficiently good, even the planet starts arriving slightly early or late. NIST notes that Earth's rotational time is irregular enough that coordinated universal time has historically required occasional leap seconds to remain close to astronomical time. This does not mean the Moon sometimes forgets which direction it is supposed to push Earth. The long-term tidal effect still favours slower rotation, but many shorter-term processes can temporarily push the length of the day in either direction. Earth is not a rigid ball rotating alone in empty space. It contains a liquid outer core, a moving atmosphere, enormous oceans, changing ice sheets, groundwater, snow, and a mantle that slowly circulates. When mass moves around the planet, the rotation responds, the same conservation principle that lets a figure skater alter. Spinning speed by changing the position of their arms operates on Earth in a much more complicated form. Move large amounts of mass closer to or farther from the rotation axis, and very small changes in rotational speed can follow. Winds can exchange angular momentum with the solid Earth. Ocean currents can do the same. Motions inside the planet matter. Even seasonal changes in the atmosphere and oceans leave detectable signals in precise measurements of Earth's rotation. This is why saying that Earth is slowing down does not mean every individual day must be longer than the one before it. The long-term trend and the short-term behaviour are different things. Over geological time, lunar tidal friction has removed rotational angular momentum from Earth and transferred it into the Moon's orbit. Over days, months, years, and decades, atmospheric circulation, ocean movement, core dynamics, and shifts in surface mass can make Earth's rotation wander around that trend. A particular modern day may therefore be fractionally shorter than average, even though the broad history of the planet runs from faster rotation towards slower rotation. It is similar to walking slowly downhill while occasionally taking a step upward. One upward step does not mean the overall journey has reversed. Climate-related changes have now become measurable as part of this rotational story. When glaciers and ice sheets lose mass, much of that water eventually enters the oceans and is redistributed around the planet. Groundwater extraction can also move water from underground storage into rivers and seas. Changing where that mass sits changes Earth's moment of inertia and can slightly alter both the position of the rotation axis and the length of the day. NASA reported in 2024 that studies using more than a century of observations found that melting ice, changing groundwater, and rising seas are contributing to changes in polar motion and are adding to the long-term lengthening of the day. The effect remains extremely small in everyday terms, but it is measurable, which is a remarkable reminder that processes occurring at Earth's surface can influence the rotation of the entire planet. The analogy with a spinning skater works particularly well here. A skater rotating with arms held close spins faster. Move the arms outward and the rotation slows. When ice that was concentrated relatively near the poles melts and water spreads through the global ocean, some masses effectively moved farther from Earth's rotation axis. The planet responds with a tiny slowing. The real calculation is far more complicated because water does not spread evenly. The crust responds to changing loads, and the oceans and atmosphere are constantly moving. But the underlying idea is familiar. Earth's day is not controlled by one mechanism. The Moon provides the dominant long-term tidal break, while mass moving within the Earth system creates smaller variations layered on top. Even earthquakes can produce theoretical changes in the length of the day because they rearrange mass inside Earth. A major earthquake shifts enormous blocks of crust by meters, which sounds dramatic until compared with a planet containing around 6 sextillion metric tons of material. The resulting rotational change is normally measured in millionths of a second or less. No one leaves an earthquake saying that lunch arrived noticeably earlier because Earth changed speed. Still, instruments and calculations are sensitive enough to detect or estimate these effects. The rotation we experience as completely steady is actually the combined result of countless moving systems. The atmosphere is particularly important over shorter periods. Powerful winds carry enormous quantities of air around the globe. When atmospheric circulation changes, angular momentum can move between the air and the solid Earth. If the atmosphere gains a little angular momentum in one pattern of motion, the solid planet can respond by rotating slightly differently. Ocean currents participate in similar exchanges. Seasonal changes therefore appear in precise records of the length of day. Earth's rotation speeds up and slows down by tiny amounts as the planet moves through the year, rather like an unimaginably large clock whose gears are made from winds, currents, tides, rock, ice and liquid metal rather than brass. For people keeping time, this creates an unusual problem. Atomic clocks can count seconds with extraordinary stability, while the rotating Earth refuses to produce exactly the same astronomical day forever. The International Time System, called UTC, has therefore historically been adjusted using leap seconds so that atomic time does not drift too far away from time based on Earth's actual rotation. When needed, an extra second has been inserted at the end of a June or December day. Instead of going directly from 23:59:59 to midnight, the official sequence briefly includes 23:59:60. The first leap second was added in 1972, and the most recent one so far was inserted on December 31st, 2016. The adjustments exist because atomic clocks are far more regular than Earth's rotation. That is a wonderfully modern consequence of an ancient problem. More than 4 billion years ago, the Moon began altering Earth's rotation through tides. Today, international timekeepers occasionally have to account for the fact that our clocks can measure time more uniformly than Earth can rotate. The early planet needed no correction because nothing was trying to synchronize computer networks, navigation systems, financial transactions, scientific observatories, and communication satellites to one common timescale. Earth simply turned at whatever rate physics gave it. Human civilization arrived much later and decided that the planet should ideally cooperate with an exact schedule. The Moon itself provides one of the clearest measurements showing that the tidal interaction continues. Laser ranging experiments measure the Earth-Moon distance with remarkable precision by sending laser pulses from Earth toward retroreflectors on the lunar surface and timing their return. These observations show that the Moon is currently receding from Earth at an average rate of roughly 3.8 centimeters per year. That is about the rate at which fingernails grow, which does not seem like the beginning of an astronomical drama. Yet the direction is the same one the Moon has followed for most of its history, outward. The modern rate cannot simply be projected backward unchanged because tidal dissipation has varied enormously as Earth's oceans and continents changed, but the ongoing recession is direct evidence that angular momentum is still being transferred from Earth's rotation into the Moon's orbit. The effect on the Moon's appearance during one lifetime is completely invisible. Someone could carefully photograph the full Moon every month for 80 years and would not see it becoming noticeably smaller because of orbital recession. Geological time is required for the difference to matter visually. Millions of years from now, the Moon will be farther away and will appear slightly smaller on average. One consequence is that total solar eclipses like the ones possible today are temporary features of Earth-Moon history. At present, the apparent sizes of the Sun and Moon happen to be similar enough that the Moon can sometimes cover the solar disk almost perfectly. As the Moon recedes, it gradually becomes too small in the sky to produce the same kind of total eclipse. Far enough in the future, observers would see only annular eclipses, with a bright ring of the Sun remaining visible around the Moon. The same outward movement also means the lunar month continues to lengthen. A satellite in a larger orbit takes longer to complete that orbit. At the same time, Earth's day is slowly lengthening. Both of the natural cycles humans use to construct early calendars are therefore changing together, though far too slowly to disturb any calendar you own. The Moon takes longer to orbit, and Earth takes longer to rotate. The ratios between days, months, and years are not permanent mathematical constants. They are evolving astronomical relationships. If we could travel millions of years into the future while somehow ignoring every other change to Earth, a day would be slightly longer than it is now. Travel hundreds of millions of years and the difference could become more noticeable, though predicting the exact day length becomes difficult because future continents, oceans, climate and tidal resonance will affect the rate of breaking. The continents will not remain where they are. New ocean basins may open, old ones may close, and another supercontinent may eventually assemble. Those changes could increase or decrease the efficiency of tidal dissipation. The moon will continue moving outward, weakening its tidal forcing at the same time. There is therefore no simple timetable telling us that Earth will reach exactly 25 hours on a particular date far in the future. In an idealized Earth-Moon system allowed to continue for an extremely long time, tidal evolution would push toward mutual locking. The moon is already tidally locked to Earth, which is why nearly the same lunar hemisphere always faces us. Earth is not locked to the moon because our planet still rotates much faster than the moon travels around it. If the system could evolve undisturbed for long enough, Earth's rotation would continue slowing until one rotation matched one lunar orbit. Earth would then keep the same side facing the moon, and the moon would remain in roughly the same region of the sky for observers on that side of Earth. From the opposite hemisphere, the moon would never appear at all. From the hemisphere facing it, the moon would hang almost permanently in place, while the entire Earth-Moon pair continued orbiting the Sun. A day, in the old rotational sense, would then be enormously longer than 24 hours. But this tidy endpoint is more useful as an explanation of tidal physics than as a realistic forecast for Earth. The Sun will change dramatically on shorter astronomical timescales than the time needed for the present Earth-Moon system to reach that final state. As the Sun ages, it will gradually brighten, profoundly affecting Earth's climate, and eventually evolve into a red giant. Long before mutual tidal locking could provide anyone with a very long weekend, the planet would face much larger problems. For the moment, the important future is not billions of years away, but the continuation of a process already visible today. The moon rises at approximately the distance created by billions of years of tidal evolution. The oceans rise and fall partly because of its gravity. The planet flexes, energy is dissipated, Earth's rotation changes by tiny amounts, the moon moves outward by centimeters. Nothing about the scene looks dramatic because we are watching the process at normal speed. That is the main difficulty with understanding Earth's rotational history. Human experience is tuned to seconds, days, seasons, and perhaps decades. Geological processes often require us to think in millions of years. An effect that seems completely negligible during one lifetime can remake an entire planetary system when allowed to continue long enough. A few centimeters per year sounds insignificant. A fraction of a millisecond added to a day sounds even less impressive. But the world with a 5-hour rotation was not transformed by one enormous breaking event. It was transformed by persistent small effects operating over extraordinary spans of time. Picture that early Earth again, but now imagine the entire sequence rather than one frozen scene. The young planet spins rapidly beneath a nearby moon. The surface is hot and unstable. As Earth cools, oceans appear. Strong tides move through those oceans and deform the planet. The moon pulls on the tidal bulges and takes angular momentum from Earth's spin. The moon moves outward. The day becomes longer. The tides weaken overall, though changing ocean geography sometimes makes tidal dissipation more efficient and sometimes less. Continents form, move, collide, and break apart while the rotation continues changing. Life appears. The atmosphere gains oxygen. Complex cells evolve. Animals enter the seas. Plants spread onto land. Forests grow. Dinosaurs arrive and disappear. Mammals diversify. Humans appear extremely late. Look at the 24-hour day around them and naturally assume that this is simply how Earth works. It is only when we examine rocks, fossils, orbital mechanics, tides, and precise modern measurements that the larger picture becomes visible. 24 hours is not Earth's permanent identity. It is its current rotational state. The early planet turned much faster, and the future planet will turn more slowly. We happen to live at one point along that changing curve. This also gives a slightly different meaning to the ordinary experience of watching the moon. The moon is often treated as a quiet background object, useful for lighting landscapes, creating phases, producing eclipses, and giving people something bright to notice when taking the rubbish out at night. But it has been physically changing Earth since near the beginning of the planet's history. The length of the day you experience today is partly the result of that interaction. The pace at which sunrise followed sunrise during the evolution of life was partly shaped by it. Even the fact that our year contains roughly 365 days rather than several hundred more is connected to the billions of years during which the moon helped slow Earth's rotation, and yet the moon did not act alone. Earth's oceans determined how much tidal energy could be dissipated. Continents changed the geometry. The mantle and crust flexed. The atmosphere exchanged angular momentum with the surface. Ice shifted. Water moved. The interior circulated. What looks from space like one simple spinning sphere is really a collection of interacting systems, all contributing small adjustments to the rotation. That may be the most useful thing to remember the next time a day feels too short. There really was a time when Earth's days were vastly shorter than ours. A 5-hour rotation would make our modern 24-hour schedule look generous. Sunrise, sunset, night, and another sunrise could all pass within the span of one long modern afternoon. There would have been no extra time to notice, of course, because anything living under such a cycle would simply treat it as normal. Our own 24 hours feel normal for exactly the same reason. We were born into them. So take another look at the clock where you are, just as we did when this journey began. Perhaps it is later now. Maybe the numbers have moved farther than expected while we travelled through billions of years of Earth's history. The clock is counting regular seconds, but beneath it the actual planet is performing something slightly less perfect. Earth is rotating, wobbling, responding to winds and oceans, flexing beneath the moon's gravity, and continuing the slow mechanical change that began when the solar system was young. If you found this journey soothing, interesting, or useful company while winding down, you can give the video a like and subscribe to Just About Earth. It helps this quiet space reach other people who might enjoy discovering that even something as ordinary as the length of a day has a history stretching back to giant impacts and a moon hanging far closer than it does now. For tonight, though, you do not need to measure any of those changes. The moon will move outward only an unimaginably small amount while you sleep. Earth's rotation will remain close enough to 24 hours that tomorrow's clocks will behave exactly as expected. The ancient 5-hour world is gone, and the slower Earth beneath us has plenty of time for one more night. Sleep well, wherever you are listening from, and when morning arrives, remember that the long, unhurried sunrise we take for granted is something our planet spent billions of years learning how to provide.